To imagine a world so frozen, so vast it swallows even light. Across the ice shapes twist in the snow. Creatures blink with ancient eyes. The wind howls with whispers. Stories of towering glaciers, strange sounds that echo through the white, shadows that should not exist. Scientists dig into the earth to explore, only to find the impossible. Giant mammoths preserved in ice, lost forests buried deep, zones so cold we barely have names for them. In ancient times, the mysterious Great Freeze reshaped the world, a force stronger than any storm with no clear end. What caused it? No one truly knows. Even now, we've explored space more than our own past ice ages. What else waits, silent and unseen, in the endless white? Before we step back into this icy era, let us know where you're watching from and what time it is for you. Then settle in as we uncover the mysteries hidden in the lost prehistoric ice age. The term Ice Age often brings to mind a single, long period when much of the Earth was covered in vast sheets of ice, a time when woolly mammoths roamed and early humans huddled in caves. While this image is largely accurate for the most recent such period, it is important to understand that an ice age is not a singular event in Earth's long history. Instead, the planet has experienced multiple ice ages, each lasting for millions of years and punctuated by shorter, warmer spells. An ice age, in its simplest definition, is a long period of time when the Earth's climate is significantly colder than usual, leading to the expansion of large ice sheets and glaciers across continents, particularly in the polar and high-latitude regions. These massive ice formations are not static. They grow and shrink over thousands of years, responding to subtle shifts in global temperatures. During an ice age, the world transforms dramatically. What we now recognise as lush forests or sprawling deserts might have been buried under kilometres of ice. The sheer volume of water locked up in these ice sheets causes global sea levels to drop significantly, sometimes by more than 100 metres. This drop in sea level exposes vast areas of continental shelf, creating land bridges that connect continents previously separated by water. For instance, during the most recent major ice age, a land bridge known as Beringia connected Asia and North America, allowing animals and early human populations to migrate between the two continents. The landscape beyond the ice sheets also changes, with vast areas becoming cold, dry tundras or steppes, supporting different types of plant and animal life than those found today. The Earth's history spans billions of years, and within this immense timescale, there have been at least 5 major ice ages, or glacial periods, each consisting of multiple cycles of advancing and retreating ice. The earliest known ice age, often referred to as the Huronian glaciation, occurred about 2,400,000,000 years ago. This was a time when the Earth was still very young, and the atmosphere was quite different from what it is today. Following this, the Cryogenian period, roughly 720 million to 635 million years ago, saw what some scientists call snowball Earth events, where ice may have covered almost the entire planet, even reaching the equator. The Andean-Saharan Ice Age took place around 450 million to 420 million years ago, followed by the Karoo Ice Age, which occurred between 360 million and 260 million years ago. Each of these ancient ice ages left its mark on the geological record, providing clues about Earth's past climate. The most recent and perhaps best understood ice age is the Quaternary Glaciation, which began about 2,600,000 years ago and continues to the present day. We are currently living in an interglacial period within this larger ice age, meaning we are in a warmer spell between colder, more intense glacial phases. The Quaternary Ice Age is characterized by repeated cycles of glacial advances when ice sheets grew and interglacial retreats when ice sheets melted back. These cycles have occurred roughly every 100,000 years during the past 800,000 years. The last glacial maximum, the peak of the most recent cold period, occurred about 20,000 years ago, when ice sheets covered large parts of North America, Europe, and Asia. The scale of these ice sheets is difficult to grasp. In North America, the Laurentide ice sheet covered most of Canada and extended into the northern United States, reaching as far south as present-day Illinois and New York. In Europe, The Scandinavian ice sheet covered much of Scandinavia, the British Isles, and parts of northern Germany and Poland. These ice sheets were not flat. They were dome-shaped, sometimes reaching thicknesses of several kilometres at their centres. The immense weight of this ice pressed down on the Earth's crust, causing the land to sink. After the ice melted, the land slowly began to rebound, a process known as isostatic rebound, which is still occurring in some areas today. Life during an ice age was challenging but not impossible. Plants and animals adapted to the harsh conditions. Many large mammals, known as megafauna, evolved thick fur, layers of fat, and specialized diets to survive the cold and scarcity of food. Iconic examples include the woolly mammoth, woolly rhinoceros, saber-toothed cat, and giant ground sloth. These animals thrived in the vast grasslands and tundras that bordered the ice sheets. Early humans also lived through these periods, developing sophisticated tools, hunting techniques, and social structures to cope with the extreme environment. They learned to use fire, make warm clothing from animal hides, and build temporary shelters, demonstrating remarkable resilience and adaptability. The end of a glacial period, or the transition into an interglacial, is marked by a gradual warming trend. As temperatures rise, the massive ice sheets begin to melt, releasing enormous quantities of fresh water into the oceans, which in turn causes sea levels to rise again. This melting process can also lead to significant changes in ocean currents and atmospheric patterns, further influencing global climate. The transition from a glacial to an interglacial period is not always smooth. There can be sudden shifts and periods of rapid warming or cooling. The study of past ice ages is crucial for understanding Earth's climate system and predicting how it might respond to future changes. By examining geological records, ice cores, and fossil evidence, scientists can reconstruct the conditions of these ancient frozen worlds and gain insights into the complex interactions between ice, oceans, atmosphere, and life. The frozen world's start was not a single beginning but a recurring chapter in Earth's dynamic story, a testament to the planet's ever-changing nature. The history of Earth's climate is not a steady, unchanging line, but rather a series of grand, slow cycles, much like the planet itself taking a deep, long breath. These cycles include periods of intense cold, known as ice ages or glacial periods, interspersed with warmer intervals called interglacials. We are currently living in an interglacial period, a relatively warm phase within a larger ice age that began millions of years ago. Understanding these cold cycles is fundamental to grasping Earth's long-term climate behaviour. They are a natural and recurring feature of our planet's existence, driven by a complex interplay of astronomical forces and terrestrial processes. The idea that Earth has experienced multiple ice ages, rather than just one, is a cornerstone of modern paleoclimatology, the study of past climates. Geologists and climate scientists have pieced together this understanding through extensive research, examining evidence preserved in rocks, sediments, and ancient ice. For example, specific rock formations like tillites, which are hardened deposits left by glaciers, provide clear indicators of past glacial activity. The presence of these tillites in regions that are now warm and temperate demonstrates that ice sheets once extended far beyond their current limits. Similarly, the unique scratches and grooves, known as striations, left on bedrock by moving glaciers offer undeniable proof of their past presence. These cold cycles are not uniform in their intensity or duration. Some ice ages have been more severe than others, with ice covering a greater proportion of the Earth's surface. The length of these cycles also varies. While the Quaternary Ice Age, our current one, has seen glacial interglacial cycles roughly every 100,000 years, for the past 800,000 years, earlier ice ages had different rhythms. For instance, before about 800,000 years ago, the cycles were shorter, occurring approximately every 41,000 years. This change in rhythm points to different dominant drivers of climate variability at different times in Earth's history. The concept of Earth's breathing cycle is a useful analogy. During a glacial phase, the planet inhales vast amounts of water from the oceans, locking it up in massive continental ice sheets. This causes global sea levels to drop significantly, sometimes by more than 100 meters. As the ice sheets expand, they reflect more sunlight back into space, leading to further cooling, a positive feedback loop. The atmosphere also changes, with lower levels of greenhouse gases like carbon dioxide, which further contributes to the cooling. When the planet exhales during an interglacial phase, the ice sheets melt, releasing fresh water back into the oceans, causing sea levels to rise. Greenhouse gas levels in the atmosphere naturally increase, leading to a warming trend. This rhythmic expansion and contraction of ice, and corresponding shifts in sea level and atmospheric composition, define these cold cycles. The most recent and well-studied cold cycle is the one that has shaped the modern world. The last glacial period, often called the last glacial maximum, reached its peak about 20,000 years ago. At this time, vast portions of North America, Europe and Asia were buried under ice sheets several kilometers thick. The climate was much colder and drier globally. However, since then, Earth has been in a warming trend, transitioning into the current interglacial period, known as the Holocene epoch, which began about 11,700 years ago. This warming allowed for the retreat of the ice sheets, the rise of sea levels, and the expansion of forests and other ecosystems, ultimately paving the way for the development of human civilization as we know it. It is crucial to distinguish between an ice age as a long period with widespread ice and glacial periods as the colder phases within that larger ice age. The Quaternary Ice Age, which started about 2,600,000 years ago, encompasses many glacial and interglacial periods. We are currently in an interglacial within this ongoing ice age. This means that while we are in a warm spell, the underlying conditions that allow for the formation of large ice sheets are still present. If the natural cycles were to continue without other influences, Earth would eventually enter another glacial period in the distant future. The study of these past cold cycles is not merely an academic exercise, it provides vital context for understanding current climate change. By analysing ice cores, which contain trapped air bubbles and layers of snow that record past atmospheric conditions and temperatures, scientists can reconstruct climate history going back hundreds of thousands of years. These ice cores show clear correlations between global temperature and the concentration of greenhouse gases like carbon dioxide and methane. During glacial periods, these gas levels were significantly lower, and during interglacials they were higher. This natural variability helps scientists understand the planet's sensitivity to changes in atmospheric composition. Furthermore, these cycles highlight the Earth's inherent resilience and its capacity for dramatic climate shifts over long time scales. Life on Earth has adapted to these fluctuating conditions, with species evolving to survive both glacial and interglacial extremes. The repeated advances and retreats of ice sheets have also profoundly shaped landscapes, carving out valleys, creating lakes, and depositing vast amounts of sediment. The Great Lakes in North America, for example, are a direct result of glacial erosion and deposition. The fjords of Norway and the Finger Lakes of New York are other prominent examples of landscapes sculpted by the powerful forces of ice. The natural cold cycles of Earth demonstrate that climate is dynamic and constantly changing. These changes occur over timescales far longer than human lifespans, but their impacts are immense. Understanding the mechanisms that drive these natural cycles, such as variations in Earth's orbit, volcanic activity, and continental configurations, helps scientists distinguish between natural climate variability and human-induced changes. The Earth's breathing has been going on for eons, a testament to its complex and ever-evolving climate system. The question of why Earth experiences periods of widespread freezing, known as ice ages, is a complex one that involves the intricate dance between our planet and the Sun, as well as processes occurring on Earth itself. While the exact combination of factors can vary for each major ice age, the primary drivers for the recurring glacial and interglacial cycles within an ice age are astronomical. These are known as Milankovitch cycles, named after the Serbian scientist Milutin Milankovitch, who precisely calculated their effects in the early 20th century. These cycles describe long-term, cyclical changes in three key aspects of Earth's orbit and tilt: eccentricity, obliquity, and precession. These subtle shifts alter how much sunlight reaches different parts of the Earth, particularly at high latitudes, and how that sunlight is distributed throughout the year, especially during the crucial summer months. The first of these cycles is eccentricity, which refers to the shape of Earth's orbit around the Sun. The orbit is not a perfect circle, it is an ellipse. The degree to which this ellipse is stretched or squashed changes over a period of roughly 100,000 years. When the orbit is more elliptical, The Earth's distance from the Sun varies more throughout the year, leading to greater differences in incoming solar radiation between the closest and farthest points in the orbit. While the total amount of sunlight received over a year does not change drastically, the distribution of that sunlight can influence climate. For instance, if the Earth is farthest from the Sun during the Northern Hemisphere summer, it could lead to cooler summers, which are critical for the growth of ice sheets. The second factor is obliquity, or the tilt of Earth's axis. The Earth's axis is not straight up and down relative to its orbit. It is currently tilted at about 23.5 degrees. This tilt is what causes seasons. However, the angle of this tilt changes over a period of approximately 41,000 years, varying between about 22.1 degrees and 24.5 degrees. When the tilt is greater, the seasons are more extreme. Summers are warmer and winters are colder. When the tilt is less, the seasons are milder. For an ice age to begin or intensify, it is not necessarily the coldest winters that are most important, but rather the cool summers. If summers in the Northern Hemisphere are not warm enough to melt all the snow and ice that accumulated during the previous winter, then snow and ice can build up year after year, eventually forming large ice sheets. A smaller axial tilt leads to milder summers, which favours the preservation of snow and ice. The third and final Milankovitch cycle is precession, which describes the wobble of Earth's axis. Imagine a spinning top that is slowing down and starting to wobble. Earth's axis does something similar. This wobble changes the direction of the axis relative to the stars and, more importantly for climate, changes the timing of the seasons relative to Earth's position in its elliptical orbit around the Sun. This cycle occurs over two main periods, roughly 19,000 and 23,000 years. Precession determines when Earth is closest to the Sun, perihelion, and farthest from the Sun, aphelion, during its orbit. For example, if the Northern Hemisphere summer occurs when Earth is farthest from the Sun, aphelion, it will experience a cooler summer, which again is conducive to the growth of ice sheets because less snow melts. It is the combination and synchronization of these three cycles that are believed to be the primary triggers for the glacial and interglacial periods of the Quaternary Ice Age. When the conditions align, for instance when eccentricity is high, more elliptical orbit, obliquity is low, less tilt leading to milder summers, and Northern Hemisphere summers occur at aphelion, farthest from the Sun, the amount of solar radiation reaching the high northern latitudes during summer is reduced. This reduction in summer warmth is crucial. It means that snow and ice that fell during the winter do not fully melt away during the summer months. Over hundreds and thousands of years, this accumulated snow compacts into ice, and small glaciers grow into massive continental ice sheets. While Milankovitch cycles provide the astronomical pacemaker for ice ages, they are not the sole explanation. Terrestrial factors also play a significant role, often acting as amplifiers or dampeners of the orbital forcing. One important terrestrial factor is the configuration of continents. When continents are positioned in a way that blocks ocean currents from distributing warm water to polar regions, or when large land masses are located at high latitudes, they can facilitate the formation and growth of ice sheets. For example, the current arrangement of continents, with Antarctica over the South Pole and large land masses in the Northern Hemisphere, is considered favourable for the existence of an ice age. Another crucial terrestrial factor is the concentration of greenhouse gases in the atmosphere, particularly carbon dioxide. While changes in carbon dioxide levels are often seen as a response to glacial cycles, lower temperatures lead to lower carbon dioxide and vice versa, they also act as a powerful feedback mechanism. During periods when ice sheets are growing, natural processes can lead to a reduction in atmospheric carbon dioxide, which further cools the planet and reinforces the glacial conditions. Conversely, during warming periods, natural increases in carbon dioxide can accelerate the melting of ice. Volcanic activity can also influence climate by releasing aerosols and gases into the atmosphere, which can temporarily cool the planet by blocking sunlight. The growth of ice sheets itself creates a positive feedback loop known as the ice albedo feedback. Albedo refers to the reflectivity of a surface. Ice and snow are highly reflective, meaning they bounce a large percentage of incoming sunlight back into space. As ice sheets grow, they cover more of the land, increasing the Earth's overall albedo. This increased reflectivity means less solar energy is absorbed by the Earth's surface, leading to further cooling, which in turn allows more ice to form, perpetuating the cycle. This feedback mechanism is a powerful amplifier of the initial cooling triggered by Milankovitch cycles. The process of Earth freezing is therefore a complex dance involving astronomical rhythms that set the stage and terrestrial factors that amplify or modify the climate response. It is not a sudden event, but a gradual accumulation of snow and ice over thousands of years, driven by subtle, long-term changes in the amount and distribution of sunlight reaching the planet's surface. Understanding these mechanisms is vital for comprehending Earth's past climate and for putting current climate changes into a broader geological context. The Earth's journey around the Sun is not perfectly steady, nor is its tilt or wobble in space. These small but predictable changes in our planet's movement over very long periods greatly affect how much sunlight reaches different parts of the world. This uneven sunlight, called insolation, is a main driver of the Earth's natural shifts into and out of ice ages. These cycles are known as Milankovitch cycles, named after the Serbian scientist Milutin Milankovitch, who refined earlier ideas in the early 20th century. He calculated how these orbital variations would change the amount of solar radiation received at different latitudes and seasons. His theory became a cornerstone for understanding the rhythms of past climate changes. There are three main ways the Earth's orbit and tilt change. The first is called eccentricity, which describes the shape of the Earth's path around the Sun. This path is not a perfect circle. It is an ellipse, like a slightly squashed circle. Over a period of about 100,000 years, this ellipse changes its shape. Sometimes it is more circular, and sometimes it is more stretched out, or elliptical. When the orbit is more elliptical, the Earth's distance from the Sun varies more greatly throughout the year. This means that at some points in its orbit, Earth will be significantly closer to the Sun, and at others, much farther away. While the total amount of sunlight reaching Earth over a whole year changes only slightly due to eccentricity, its effect becomes more important when combined with other cycles, particularly in how it influences the severity of seasons depending on when the Earth is closest or farthest from the Sun. For example, if the Northern Hemisphere summer occurs when Earth is farthest from the Sun during a more eccentric orbit, that summer will be cooler, which is a key condition for allowing winter snow and ice to persist. The second change is called obliquity, or the tilt of the Earth's axis. Imagine the Earth as a spinning top. Its axis, the imaginary line it spins around, is tilted relative to its orbit around the Sun. This tilt is what causes seasons. If the axis were not tilted, there would be little seasonal change. The angle of this tilt is not fixed. It changes over a period of about 41,000 years. It varies between about 22.1 degrees and 24.5 degrees. When the tilt is greater, the seasons become more extreme. Summers are hotter, and winters are colder in both hemispheres. When the tilt is smaller, the seasons are milder. For the growth of large ice sheets, particularly in the northern hemisphere, a smaller tilt is important. A smaller tilt means that high-latitude summers are cooler. This cooler summer prevents all the snow that fell in winter from melting. If the snow does not melt completely each summer, it can accumulate year after year, eventually compacting into glacial ice. So, periods of lower obliquity are often linked to the start of northern hemisphere glaciations. The third change is called precession, or the wobble of the Earth's axis. Just like a spinning top slows down and its top starts to wobble in a circle, the Earth's axis also wobbles. This wobble changes the direction the Earth's axis points in space. This cycle takes about 23,000 years to complete. The most important effect of precession is that it changes when the Earth is closest to the Sun, perihelion, and farthest from the Sun, aphelion, during a given year. For example, right now, the Earth is closest to the Sun during the Northern Hemisphere winter. This makes Northern Hemisphere winters milder than they would be otherwise. In about 11,500 years, due to precession, the Earth will be closest to the Sun during the Northern Hemisphere summer. This would make Northern Hemisphere summers hotter. The timing of perihelion and aphelion relative to the seasons significantly impacts the intensity of the seasons. For ice sheet growth, a key condition is cooler summers in the Northern Hemisphere. If precession causes the Northern Hemisphere summer to occur when the Earth is farthest from the Sun, then those summers will be less intense, again allowing winter snow to survive and accumulate. It is the combination of these three cycles that is most important for driving ice ages. Milankovitch theory suggests that glacial periods begin when the Northern Hemisphere receives less sunlight during its summers. This happens when the Earth's orbit is more elliptical, eccentricity, when its tilt is smaller, obliquity, and when the northern hemisphere summer occurs when the Earth is farthest from the Sun, precession. When these conditions align, the northern hemisphere summers are not warm enough to melt all the snow that falls during the winter. This allows snow to build up year after year, forming vast ice sheets. Conversely, interglacial periods, the warmer times between ice ages, occur when northern hemisphere summers receive more sunlight, leading to the melting of glaciers. Scientists have found strong evidence supporting the Milankovitch theory by studying ice cores and ocean sediments. Ice cores drilled from Antarctica and Greenland contain trapped air bubbles that preserve tiny samples of Earth's ancient atmosphere, including carbon dioxide levels and isotopes of oxygen that reveal past temperatures. These records show clear cycles of warming and cooling that match the periods of the Milankovitch cycles over the past 800,000 years. Ocean sediments also contain fossilized remains of tiny marine organisms whose shells can tell us about past sea surface temperatures and ice volume, further confirming the orbital forcing of climate. While these orbital changes do not create enough energy change on their own to fully explain the vast swings in global temperature seen between ice ages and warm periods, they act as the initial trigger. They cause small changes in solar energy that are then amplified by other processes, such as changes in atmospheric greenhouse gases and the reflectivity of Earth's surface. The Earth's surface is not a solid, unbroken shell, but is made up of several large plates that slowly move over the planet's mantle. This process is called plate tectonics, and it describes how continents drift across the globe over millions of years, collide to form mountain ranges, and pull apart to create new oceans. These incredibly slow movements, typically at speeds of a few centimeters per year, have a profound impact on Earth's climate over geological timescales, playing a significant role in setting the conditions for whether ice ages can occur. The positions of continents influence global ocean currents and atmospheric circulation patterns, which are key to distributing heat around the planet. One of the most significant ways moving continents affect climate is by changing the flow of ocean currents. Ocean currents are like giant conveyor belts that transport vast amounts of heat from the equator towards the poles and cold water back towards the equator. If continents are positioned in a way that blocks these warm currents from reaching high latitudes, those regions can become much colder. A classic example of this is the formation of the Antarctic circumpolar current. About 34 million years ago, as the supercontinent Gondwana broke apart, Antarctica separated from South America and Australia. The Drake Passage, a narrow stretch of water between South America and Antarctica, and the Tasmanian Gateway between Australia and Antarctica opened up. Once fully open, these passages allowed a strong ocean current to flow unimpeded around Antarctica. This circumpolar current effectively isolated Antarctica from warmer ocean waters, leading to its deep freeze and the formation of its massive ice sheet, marking the beginning of the current Cenozoic Ice Age. Similarly, the closing or opening of other ocean gateways can redirect ocean currents, either promoting or preventing the delivery of heat to polar regions, thus influencing global temperatures. For instance, the formation of the Isthmus of Panama about 3 million years ago largely cut off the direct flow of water between the Atlantic and Pacific Oceans, altering ocean circulation in the Atlantic and potentially contributing to the intensification of Northern Hemisphere glaciation during the late Cenozoic. Beyond ocean currents, the placement of continents also impacts atmospheric circulation. When large land masses are located near the poles, they provide a stable surface upon which large ice sheets can form and grow. If the poles were entirely covered by open ocean, it would be much harder for vast stable ice sheets to develop, because ocean water stores heat differently and is constantly moving. The presence of land at high latitudes provides a foundation for snow and ice to accumulate. For example, during the late Paleozoic Ice Age, from about 360 million to 260 million years ago, the supercontinent Gondwana was situated directly over the South Pole, providing the necessary land mass for a major ice sheet to form there. The uplift of large mountain ranges through continental collisions also affects atmospheric patterns. Mountain ranges can block prevailing winds, create rain shadows, and influence global atmospheric circulation, which in turn affects regional climates and precipitation patterns crucial for snow accumulation or melt. Furthermore, the creation of large mountain ranges increases the amount of exposed rock that can undergo weathering. The chemical weathering of silicate rocks, a process where rocks react with carbon dioxide from the atmosphere, effectively removes carbon dioxide from the air. Over millions of years, extensive mountain building can significantly reduce atmospheric carbon dioxide levels, leading to a global cooling effect. Past ice ages provide clear illustrations of the deep connection between continental positions and climate. The Huronian Ice Age, which occurred approximately 2.4 billion to 2.1 billion years ago, is one of the earliest known and longest-lasting glacial periods. While the exact continental configuration of that ancient time is difficult to reconstruct precisely, theories suggest that continents may have been arranged in a way that allowed for extensive ice coverage, possibly exacerbated by early atmospheric changes. Much later, the Cryogenian Ice Age, spanning from about 720 million to 635 million years ago, is famous for the snowball Earth events, where it is believed that ice sheets extended almost to the equator. During this period, the supercontinent Rodinia was positioned near the equator. This equatorial landmass could have led to increased rainfall and weathering of rocks, drawing down large amounts of carbon dioxide from the atmosphere. Additionally, the arrangement of continents might have created ocean basins that were less effective at transporting heat, leading to widespread cooling that spiraled into a global freeze through strong feedback loops. The current Cenozoic Ice Age, which began roughly 34 million years ago, is another prime example. It started with the isolation of Antarctica and was intensified over millions of years as land masses in the northern hemisphere, such as North America and Eurasia, drifted towards the North Pole. This geographical arrangement with land surrounding the Arctic Ocean allows for the formation of significant ice sheets in the northern hemisphere during periods of favourable orbital conditions. Without these land masses, it would be much more difficult for the large continental ice sheets, like those that covered North America and Europe during the last glacial maximum, to form. Thus, the incredibly slow dance of continents over geological timescales fundamentally shapes the Earth's climate by altering ocean and atmospheric circulation, influencing the distribution of heat and creating the very surfaces upon which vast ice sheets can accumulate and persist. The composition of Earth's atmosphere, particularly the concentration of certain gases, plays a critical role in regulating the planet's temperature and, by extension, the presence or absence of widespread ice. These gases are known as greenhouse gases because they trap heat in the atmosphere, similar to how glass traps heat in a greenhouse. Without them, Earth would be a much colder, uninhabitable planet. Among these gases, carbon dioxide, or CO2, is one of the most important over long geological timescales in influencing the planet's overall climate state, including its shifts into and out of ice ages. Carbon dioxide enters and leaves the atmosphere through various natural processes, known as the carbon cycle. Over millions of years, volcanic eruptions release significant amounts of carbon dioxide into the atmosphere. This acts as a long-term source of the gas. On the other hand, the weathering of rocks, particularly silicate rocks, acts as a long-term sink for carbon dioxide. When rain, which is slightly acidic due to dissolved carbon dioxide, falls on rocks, it reacts with the minerals, slowly breaking them down. This chemical reaction pulls carbon dioxide out of the atmosphere and eventually stores it in the oceans and ocean sediments. The rate of this weathering process can change. For example, if there are more exposed rocks, such as during periods of mountain building, more carbon dioxide can be removed from the atmosphere. Oceans also play a crucial role, as they can absorb and release vast amounts of carbon dioxide, acting as a large reservoir that exchanges gas with the atmosphere. Furthermore, biological processes like photosynthesis by plants remove carbon dioxide from the air, while the respiration of living things and the decay of dead organic matter release it back. The concentration of carbon dioxide in the atmosphere directly impacts global temperatures. When atmospheric carbon dioxide levels are low for extended periods, the Earth's natural greenhouse effect is weakened, leading to global cooling. This cooling can be a primary factor in pushing Earth into an icehouse state, where conditions are favourable for widespread glaciation. For example, during some past ice ages, geological evidence suggests that episodes of intense mountain building, such as the uplift of the Himalayas, might have led to increased silicate weathering, drawing down atmospheric carbon dioxide over millions of years and contributing to the long-term cooling trend that allowed for major ice sheet expansion. Conversely, high levels of atmospheric carbon dioxide can prevent ice ages from occurring or cause existing ice sheets to melt, leading to warmer, greenhouse climate states, even if other factors might otherwise favour cooling. The Earth has seen periods in its deep past where carbon dioxide levels were many times higher than today, and during those times, there were no polar ice caps. A powerful amplifying mechanism in climate change, strongly linked to both carbon dioxide levels and the presence of ice, is the albedo feedback. Albedo refers to how much sunlight a surface reflects. Surfaces that are bright and white, like ice and snow, have a very high albedo, meaning they reflect a large percentage of incoming sunlight back into space. Darker surfaces like oceans or bare land have a much lower albedo and absorb more sunlight. This difference in reflectivity creates a positive feedback loop that can accelerate climate changes. When the Earth cools and ice sheets begin to grow, the increased white surface area reflects more solar radiation. This reflection means less energy is absorbed by the Earth, leading to further cooling. This additional cooling promotes even more ice growth, which in turn reflects more sunlight, creating a cycle that accelerates the cooling trend and the expansion of ice. The reverse is also true. If the Earth begins to warm, perhaps due to increasing carbon dioxide or changes in orbital cycles, ice and snow begin to melt. As ice melts, darker land and ocean surfaces are exposed. These darker surfaces absorb more sunlight, causing further warming. This additional warming leads to more ice melt, completing the positive feedback loop and accelerating the warming trend and the retreat of ice. Water vapor is another potent greenhouse gas, but unlike carbon dioxide, its concentration in the atmosphere is largely controlled by temperature. Warmer air can hold more water vapor. Thus, water vapor acts primarily as a feedback mechanism. An initial warming, from carbon dioxide or orbital changes, increases water vapor, which amplifies the warming. Similarly, an initial cooling reduces water vapor, which amplifies the cooling. Crucial evidence for the link between atmospheric gases and ice ages comes from ice cores drilled from polar regions, such as those in Antarctica. These ice cores contain tiny bubbles of ancient air, trapped when the snow compacted into ice over hundreds of thousands of years. By analysing the gas composition in these bubbles, scientists can directly measure past atmospheric concentrations of carbon dioxide and other greenhouse gases. These records reveal a remarkable correlation. Periods of low atmospheric carbon dioxide consistently align with cold glacial periods, and periods of high carbon dioxide align with warm interglacial periods. For example, over the past 800,000 years, carbon dioxide levels have varied in sync with the Earth's temperature changes and the advance and retreat of ice sheets. These variations in carbon dioxide are not the sole cause of ice ages, but act as powerful amplifiers. Small initial changes in the amount of sunlight received due to Earth's orbital variations, Milankovitch cycles, can trigger a slight warming or cooling. This slight change then influences the carbon cycle, causing carbon dioxide to be released from or absorbed by the oceans, or altering the rate of rock weathering. These changes in carbon dioxide, along with the powerful albedo feedback from growing or shrinking ice sheets, then amplify the initial orbital forcing, leading to the large-scale climatic shifts characteristic of ice ages. During the vast stretches of time known as ice ages, the Earth transformed into a dramatically different place. Huge parts of the continents were buried under colossal masses of ice, known as ice sheets or continental glaciers. These were not simply large patches of snow, they were immense, slow-moving bodies of solid ice, covering areas larger than many modern countries. To understand the prehistoric ice age, one must first grasp the sheer scale and immense power of these frozen giants. Imagine a sheet of ice so enormous that it stretched across an entire continent. During the last major ice age, which reached its peak around 20,000 years ago, two primary ice sheets dominated the northern hemisphere. In North America, the Laurentide ice sheet covered most of Canada and extended deep into what is now the United States, reaching as far south as the states of Illinois and Ohio. To the west, it merged with the Cordilleran ice sheet, which draped over the Rocky Mountains. In Europe, the Fennoscandian ice sheet spread across Scandinavia, much of the British Isles, and parts of northern Germany and Poland, reaching into western Siberia. Smaller ice sheets also existed in other high-latitude regions and mountain ranges around the world, but these two were the titans. The size of these ice sheets was truly staggering. They were not just wide, but also incredibly thick. At their centres, the ice could be several kilometres deep. Picture mountains, even tall ones, completely submerged beneath the ice, with only the highest peaks, known as nunataks, poking through like islands in a frozen sea. For instance, the Laurentide ice sheet was estimated to be more than 3 kilometres thick over parts of Hudson Bay in Canada. This immense thickness meant that the ice sheets created their own local weather systems, influencing wind patterns and temperatures far beyond their immediate edges. The top of the ice sheet would have been a desolate, windswept plateau, high above the original land surface. The weight of these enormous ice sheets was almost unimaginable. A single cubic metre of ice weighs about 900 kilograms. When you multiply that by billions of cubic meters, the total weight becomes astronomical. This colossal burden pressed down on the Earth's crust, causing the land beneath the ice to slowly sink, a process known as isostatic depression. Areas that were under the thickest parts of the ice sheets, like Hudson Bay, were pushed down by hundreds of meters. After the ice melted, this depressed land began to slowly rise again, a process called isostatic rebound, which is still occurring in some areas today, thousands of years after the ice disappeared. This slow uplift can even cause small earthquakes as the Earth's crust adjusts. A significant consequence of so much water being locked up in these massive ice sheets was a dramatic drop in global sea levels. All the water that formed the ice had to come from somewhere, and that somewhere was the oceans. During the peak of the last ice age, global sea levels were about 120 meters lower than they are today. This massive drop exposed vast areas of continental shelf, creating new land. The most famous example is the Bering Land Bridge, which connected Asia and North America, allowing animals and early humans to migrate between the continents. Other land bridges appeared between Britain and mainland Europe, and between Southeast Asia and Australia. Coastlines were entirely different, and many areas that are now submerged under shallow seas were once dry land. These vast ice sheets also profoundly influenced the global climate. Their bright white surfaces reflected a huge amount of sunlight back into space, helping to keep the planet cooler. This reflection, known as the albedo effect, reinforced the cold conditions that allowed the ice sheets to grow in the first place. The presence of such large ice masses also altered atmospheric circulation patterns, steering winds and storms in new directions. Ocean currents, which play a crucial role in distributing heat around the globe, were also affected by the changing sea levels and the physical barriers posed by the ice sheets. For example, the North Atlantic Ocean circulation was significantly different, leading to colder conditions in certain regions. While the detailed formation and movement of glaciers will be discussed in later sections, it is important to understand that these ice sheets grew over tens of thousands of years from the accumulation of snow that did not melt in summer. As layer upon layer of snow compacted, it transformed into solid ice, gradually expanding outwards from centres of accumulation. This outward flow, driven by the immense weight of the ice, was slow but incredibly powerful. The sheer mass of the ice meant that it could overcome almost any obstacle in its path, slowly but relentlessly grinding and sculpting the land beneath it. Scientists have pieced together the story of these prehistoric ice sheets by studying the marks they left on the landscape. Features like U-shaped valleys, drumlins, elongated hills of till, eskers, winding ridges of sand and gravel, and moraines, ridges of rock and sediment deposited by the ice, are all clear evidence of past glaciation. Large boulders, known as glacial erratics, found far from their original source, also tell a tale of ice sheet movement. By mapping these features and analysing sediments, scientists can reconstruct the extent and thickness of ancient ice sheets, providing a window into Earth's frozen past. Life during the Ice Age adapted to the presence of these massive ice sheets. While the ice itself was barren, the areas at its edges, such as the vast tundra plains, supported a variety of hardy plants and large animals like woolly mammoths, woolly rhinoceroses, and giant deer. These creatures thrived in the cold, open environments, grazing on the tough vegetation that could survive the harsh conditions. Early humans also lived alongside these animals, adapting their hunting and survival strategies to the challenging climate. They found refuge in ice-free areas, often near the margins of the ice sheets, where resources were available. The period known as the last glacial maximum, around 20,000 years ago, represents the peak extent of these ice sheets. At this time, the world looked vastly different from today, with vast white expanses dominating the northern continents. Understanding the scale and power of these prehistoric ice sheets is fundamental to comprehending the environmental, climatic, and biological changes that characterize the ice ages and shape the modern world. The ice sheets were not just passive features, they were active agents of change, profoundly altering the planet's geography, climate, and life. Even today, the Greenland and Antarctic ice sheets are remnants of these ancient titans, holding clues to Earth's past and influencing its future. The formation and growth of glaciers, including the enormous prehistoric ice sheets, is a slow and gradual process that begins with something as simple as a snowflake. It is a testament to the power of persistent cold and accumulation over vast stretches of time. For a glacier to form, two main conditions must be met. There must be enough snowfall, and that snow must not completely melt away during the warmer months. This second condition is crucial, as it allows snow to accumulate year after year, building up the raw material for ice. The journey from a delicate snowflake to dense glacial ice begins in areas where temperatures remain consistently low, typically at high latitudes or high altitudes. When snow falls in these regions, it lands on previous layers of snow. If the summer is not warm enough to melt all of this accumulated snow, a new layer is added on top the following winter. This process repeats over many seasons, sometimes hundreds or even thousands of years. Each new snowfall adds weight and pressure to the layers beneath it. As new snow piles up, the older snow beneath undergoes a transformation. The weight from above compresses the lower layers. This compression, combined with slight melting and refreezing that can occur even in cold temperatures, causes the delicate six-sided snowflakes to change their shape. Their intricate arms break off, and they become more rounded and granular. The air pockets between the snowflakes are squeezed out, and the snow becomes denser. This intermediate stage, where the snow has lost its original fluffy texture and become more compact and granular, is called firn. Firn looks like coarse, icy sand. The transformation from snow to firn is a critical step. The density of firn is significantly higher than fresh snow. As more and more snow accumulates on the surface, the firn layers are buried deeper and deeper. The pressure from the overlying snow and firn continues to increase. This immense pressure forces out even more of the trapped air. The remaining air pockets become smaller and isolated, often taking on a spherical shape. As the air is expelled, the firn gradually transforms into solid, interlocking ice crystals. This is true glacial ice. One noticeable characteristic of glacial ice is its often striking blue colour. This blue hue is not due to impurities but is a result of the ice itself. When light passes through thick glacial ice, the ice absorbs the red and yellow parts of the light spectrum while the blue light is scattered and reflected, making the ice appear blue. This is similar to why deep ocean water looks blue. It's about the absorption and scattering of light wavelengths. The deeper the ice and the fewer the air bubbles, the more intense the blue colour tends to be. The time it takes for snow to transform into glacial ice varies depending on factors like temperature and snowfall rates. In areas with very high snowfall and relatively warm glacial ice, where temperatures are close to the melting point, this process can happen relatively quickly, perhaps within a few decades. However, in colder, drier regions, or for the deepest layers of massive ice sheets, it can take hundreds or even thousands of years for snow to fully compact into dense glacial ice. The oldest ice found in the Antarctic ice sheet, for example, is over 800,000 years old, meaning the snow that formed it fell nearly 1 million years ago. For a glacier to grow, the amount of snow accumulation must be greater than the amount of ice loss. Ice loss, known as ablation, can occur through several processes: melting at the surface or edges, evaporation, sublimation, and calving, when chunks of ice break off into water bodies. The balance between accumulation and ablation determines whether a glacier grows, shrinks, or stays the same size. If accumulation exceeds ablation over a long period, the glacier will grow and advance. If ablation exceeds accumulation, it will shrink and retreat. Every glacier has an equilibrium line or snow line. This is an imaginary boundary on the glacier's surface, where the amount of snow accumulated in a year is exactly balanced by the amount of ice lost through melting and other processes. Above the equilibrium line is the accumulation zone, where snow builds up year after year, feeding the glacier's growth. Below the equilibrium line is the ablation zone, where more ice is lost than gained, and the glacier thins. The position of this equilibrium line can shift with changes in climate, influencing the overall health and size of the glacier. The growth of massive prehistoric ice sheets involved these same fundamental processes, but on an unprecedented scale. Over tens of thousands of years during periods of sustained global cooling, snow accumulated over vast continental areas. The balance of accumulation over ablation shifted dramatically, allowing these ice masses to expand outwards from their centres. As the ice grew thicker and spread, its own presence helped to reinforce the cold conditions. The white surface reflected more sunlight, keeping the regional climate cool, which in turn allowed more snow to fall and persist, creating a powerful feedback loop that drove the expansion of the ice sheets. The internal structure of a glacier is like a layered cake, or the rings of a tree. Each year's snowfall, if it survives the summer, forms a distinct layer. As these layers are buried and compacted, they preserve information about past climates. Scientists can drill ice cores deep into glaciers and ice sheets, extracting cylinders of ice that contain trapped air bubbles, dust, pollen, and chemical signatures from past atmospheres. By analysing these layers, they can reconstruct past temperatures, atmospheric composition, and snowfall rates, providing invaluable data about the conditions that allowed these immense ice masses to grow. While a glacier or an ice sheet might appear to be a static, unchanging mass of ice, this perception is misleading. Glaciers are in fact dynamic systems that are constantly in motion, flowing slowly but powerfully under their own weight. This movement, though often imperceptible to the naked eye over short periods, is the primary force that allows glaciers to sculpt and reshape the Earth's surface over vast stretches of time. Understanding how ice moves is key to comprehending its immense power as an agent of geological change. The fundamental reason glaciers move is gravity. Just like a river of water flows downhill, a river of ice is pulled by gravity from higher elevations to lower ones. Even on seemingly flat terrain, the sheer mass and thickness of a continental ice sheet create a gentle slope on its upper surface, allowing the ice to spread outwards from its centre of accumulation. This outward push, driven by the immense weight of the ice itself, ensures that even the largest ice sheets are not truly stationary. There are two primary mechanisms by which glaciers move: internal deformation and basal sliding. Both contribute to the overall flow, though their relative importance can vary depending on the glacier's characteristics and environment. Internal deformation, also known as creep, is the process where the ice crystals within the glacier deform and slide past each other. Glacial ice, despite being solid, behaves like a very viscous, slow-moving fluid under the immense pressure of its own weight. The ice crystals are not rigid. They can change shape and slide along their internal planes. This deformation occurs throughout the entire body of the glacier, but it is most pronounced in the deeper layers, where the pressure is greatest. Imagine a deck of cards being pushed from one end. The cards slide past each other. Similarly, layers of ice within the glacier slowly slide over one another. This mechanism allows glaciers to flow even when they are frozen solid to the bedrock beneath them. Basal sliding is the second major mechanism of glacial movement. This occurs when the entire mass of the glacier slides over the ground beneath it. For basal sliding to happen, there must be a thin layer of water at the base of the glacier, acting as a lubricant. This meltwater can originate in a few ways. One way is through pressure melting. The immense pressure exerted by the thick ice can lower the melting point of ice, causing it to melt even if the temperature is slightly below 0 degrees Celsius. Another source of meltwater can be surface meltwater that trickles down through cracks and crevasses to the base of the glacier. Once this thin film of water exists, it significantly reduces friction between the ice and the bedrock, allowing the glacier to slide. Glaciers that primarily move by basal sliding are often referred to as warm or temperate glaciers because their ice is at or near its melting point throughout. Cold or polar glaciers, where the ice is frozen to the bedrock, move predominantly by internal deformation and are generally much slower. The speed at which a glacier moves can vary significantly. Typical rates range from a few centimetres per day for slow-moving valley glaciers or the central parts of large ice sheets to several meters per day for faster flowing outlet glaciers or ice streams. In rare instances, some glaciers experience surges where they can accelerate dramatically, moving tens or even hundreds of meters per day for short periods, often due to a sudden increase in basal meltwater or changes in the underlying bedrock. Several factors influence a glacier's speed. A steeper slope will naturally lead to faster movement, as gravity has a stronger pull. The thickness of the ice also plays a crucial role. Thicker glaciers exert more pressure, leading to greater internal deformation and often more basal melting, resulting in faster flow. The temperature of the ice, as mentioned, affects whether basal sliding is possible. The roughness of the bedrock beneath the glacier also matters. A smoother, slippery bed allows for easier sliding. Finally, the amount of meltwater at the base is a direct control on basal sliding speed. Scientists use various methods to measure glacial movement. Historically, stakes were placed in the ice, and their positions tracked over time. Today, more advanced techniques involve using Global Positioning System, or GPS, receivers placed on the glacier's surface which can precisely record their movement. Satellite imagery and radar interferometry also allow scientists to monitor the flow of vast ice sheets from space, providing a comprehensive view of their dynamics. The slow, persistent movement of glaciers is incredibly powerful and is responsible for dramatically reshaping landscapes. This reshaping occurs through two main processes: erosion and deposition. Glacial erosion involves the ice picking up and grinding away rock and sediment. One key erosional process is plucking, also known as quarrying. As meltwater seeps into cracks in the bedrock beneath or alongside the glacier, it freezes and expands, wedging pieces of rock loose. These loosened rock fragments then become incorporated into the base or sides of the moving glacier. The second major erosional process is abrasion. Once rocks are embedded in the ice, they act like giant sandpaper. As the glacier moves, these embedded rocks scrape, grind, and polish the bedrock beneath and beside the ice. This process leaves behind characteristic features such as glacial striations, long parallel scratches on rock surfaces, and glacial polish, smooth, shiny rock surfaces. The combined action of plucking and abrasion creates distinctive landforms. U-shaped valleys are a hallmark of glacial erosion. Glaciers, unlike rivers, fill their entire valley, widening and deepening them into a characteristic U-shape with steep sides and a flat bottom. Cirques are bowl-shaped depressions found at the heads of glacial valleys, formed by the erosive action of a small glacier or snowfield. When multiple cirques erode into a mountain from different sides, they can create sharp, knife-edge ridges called arêtes, and pointed, pyramid-shaped peaks known as horns. Fjords are long, narrow, deep inlets of the sea, formed when glacial valleys are submerged by rising sea levels after the ice melts. As glaciers move, they not only erode but also transport and deposit vast quantities of rock and sediment, collectively known as till. When the ice melts, this material is left behind, creating a variety of depositional landforms. Moraines are ridges of till deposited at the edges or terminus, end, of a glacier. Terminal moraines mark the farthest extent of a glacier's advance, while lateral moraines form along its sides, and medial moraines form when two glaciers merge. Drumlins are elongated, oval-shaped hills composed of till shaped by the overriding ice. Eskers are long, winding ridges of sand and gravel, formed by meltwater rivers flowing in tunnels beneath the ice. Outwash plains are broad, flat areas of sand and gravel deposited by meltwater streams flowing away from the glacier's front. Finally, glacial erratics are large boulders that have been transported by the ice far from their original source rock and deposited in new locations when the glacier melts. Glaciers, those immense rivers of ice, are powerful sculptors of the Earth's surface. They move slowly but with incredible force, constantly reshaping the land they cover and pass over. Imagine a colossal, unyielding mass, kilometers thick, dragging and pushing against the very bedrock beneath it. This is the essence of how ice scrapes land, transforming gentle hills into dramatic peaks and broad plains into deep basins. The process is not quick. It unfolds over tens of thousands to hundreds of thousands of years, each tiny movement contributing to monumental changes. The scale of these changes can be truly vast, affecting entire continents. The primary way glaciers reshape land is through erosion. This erosion occurs in several forms. Plucking, also known as quarrying, is a significant process. As glacial ice flows over an area, it can freeze onto fractured bedrock. When the glacier continues its forward movement, it literally pulls away blocks of rock that have become incorporated into its base. This is particularly effective where the bedrock is jointed or contains pre-existing weaknesses. The pulled-out rock fragments then become tools within the glacier, enhancing its abrasive power. It is like a giant slow-motion excavating machine, ripping out chunks of the Earth's crust. This process is especially active on the lee side of obstacles, where pressure is reduced, allowing meltwater to refreeze in cracks and exert a powerful leverage. Another key erosional process is abrasion. This is where the glacier acts like sandpaper. As the ice moves, it carries with it a vast amount of rock debris, ranging from fine silt and sand to large boulders, all frozen within its lower layers. These embedded rock fragments are dragged across the underlying bedrock, grinding and scraping away at it. This continuous grinding action polishes the rock surfaces, creates parallel scratches called striations, and produces a fine rock flour. The striations indicate the direction of the glacier's movement, providing valuable clues to past ice flow patterns. The intensity of abrasion depends on several factors, including the amount and size of the embedded debris, the hardness of the bedrock, the thickness and speed of the ice, and the amount of meltwater at the glacier's base, which can act as a lubricant, allowing the ice to slide more easily over the bedrock, increasing the effectiveness of the embedded tools. The combined effects of plucking and abrasion lead to the formation of distinctive glacial landforms. One of the most iconic is the U-shaped valley, also known as a glacial trough. River valleys are typically V-shaped because rivers carve downwards. However, when a glacier flows through a pre-existing river valley, its immense bulk and erosive power widen and deepen the valley sides and floor, giving it a characteristic parabolic or U-shaped cross-section. The valley walls are often steep and straightened, while the floor becomes broad and relatively flat. Fjords are a special type of U-shaped valley that has been flooded by the sea after the glacier retreated, common in coastal mountainous regions like Norway and New Zealand. These deep, narrow inlets with steep sides are a direct result of intense glacial scour below sea level. Cirques are another common glacial landform, representing the starting point of glacial erosion in mountainous areas. A cirque is a bowl-shaped depression with steep cliff-like headwalls and a scooped-out basin. They form when snow accumulates in a hollow, compacts into glacial ice, and then begins to move, eroding the hollow through rotational scour and plucking at the headwall. As the glacier grows and moves out of the cirque, it leaves behind this distinctive armchair-shaped depression. Often, after the ice melts, a small lake called a tarn fills the bottom of a cirque. Multiple cirques eroding into a mountain from different directions can create sharp, jagged features. Arêtes are narrow, knife-edge ridges that form between two cirques that are eroding back-to-back or between parallel glacial troughs. As glaciers on either side carve away at the mountain, they leave a sharp, thin ridge separating them. When three or more cirques erode a mountain from different sides, they can produce a sharp, pyramid-shaped peak known as a horn, with the Matterhorn in the Alps being a famous example. These features are characteristic of alpine glaciation, where individual glaciers are confined to mountain valleys. Continental ice sheets, which covered vast expanses of land during peak glacial periods, also left their mark. While they did not create U-shaped valleys or horns in the same way as alpine glaciers, their sheer weight and erosive power scraped away immense amounts of soil and weathered rock, exposing the underlying bedrock. This process is known as glacial scouring. In many parts of Canada and Scandinavia, for instance, the landscape is dominated by vast areas of exposed, smoothed bedrock, often bearing glacial striations and polished surfaces, testament to the passage of continental ice sheets. The Great Lakes in North America are a prime example of massive depressions deepened and shaped by repeated glacial advances and retreats, with the ice excavating pre-existing river valleys and basins. Similarly, the Finger Lakes in New York State are long, narrow lakes occupying glacial troughs. Glaciers also create landforms through deposition, not just erosion. As the ice moves, it transports vast quantities of eroded rock and sediment, known as till or glacial drift. When the glacier melts, this material is deposited, forming various features. Moraines are accumulations of till. Terminal moraines form at the furthest extent of a glacier's advance, marking its maximum reach. They often appear as crescent-shaped ridges. Lateral moraines form along the sides of a glacier, composed of debris that falls onto the ice from valley walls. Medial moraines form when two glaciers merge, and their lateral moraines combine to form a ridge of debris in the middle of the new, larger glacier. Ground moraines are broad, undulating sheets of till deposited beneath the glacier as it melts and retreats, creating a gently rolling landscape. Drumlins are streamlined, elongated hills made of till, shaped by the overriding ice. They are typically asymmetrical, with a blunt end facing the direction from which the glacier came, and a gentler slope pointing in the direction of ice flow. Their formation is complex, but involves the reshaping of existing till by the moving ice, often in areas where the ice flow was relatively fast and steady. Eskers are long, winding ridges of sand and gravel, often resembling railway embankments. They form from sediment deposited by meltwater rivers flowing in tunnels beneath or within the glacier. When the ice melts, these former riverbeds are left as elevated ridges. Kames are small, irregularly shaped hills or mounds composed of stratified sand and gravel, deposited by meltwater streams flowing on or at the edge of a melting glacier, often in depressions on the ice surface. Kettle lakes are depressions left behind when buried blocks of ice melt, creating hollows that fill with water. The sheer volume of material moved by glaciers is immense. They can transport everything from fine rock flour, which can turn meltwater rivers a milky colour, to enormous erratic boulders. Erratic boulders are rocks that have been transported by glaciers far from their original source, often consisting of a different rock type from the local bedrock. Their presence indicates past glacial activity and the direction of ice flow, sometimes over hundreds of kilometres. These erratics can be found resting incongruously on bedrock surfaces that are geologically distinct, serving as clear evidence of glacial transport. Beyond the immediate erosional and depositional features, glaciers have broader impacts on the landscape. They can block existing river courses, creating large proglacial lakes at their margins. When these ice dams break, they can release catastrophic floods, further reshaping the landscape downstream. The immense weight of ice sheets can also depress the Earth's crust, a process known as isostatic depression. This depression can be several hundred meters deep in areas of thickest ice. After the ice melts, the land slowly rebounds, a process called isostatic rebound, which can continue for thousands of years, affecting sea levels and creating new coastlines. This ongoing rebound is still observable in regions like Scandinavia and parts of North America. The altered drainage patterns, the creation of new lakes, and the exposure of fresh bedrock surfaces all contribute to a landscape profoundly transformed by glacial action. The legacy of ice is not just in the dramatic mountain peaks or the rolling plains, but in the very foundation of the land itself. Beyond the colossal ice sheets and the immediate zone of active glacial erosion lay vast, cold and often dry landscapes known as periglacial environments. These cold deserts were not covered by glaciers, but were profoundly shaped by the near-freezing temperatures and the repeated freezing and thawing of water in the ground. While true deserts are defined by lack of rainfall, these cold deserts were characterized by low temperatures that limited biological activity and a unique set of geological processes driven by ice in the ground. The most characteristic of these landscapes were the tundra and regions underlain by permafrost. The term cold desert refers to the low biological productivity and often sparse vegetation rather than a complete absence of water, as water is often present in the form of ice or snow. These expansive regions presented a distinct ecological and geomorphological setting during the Ice Age. The tundra is an ecosystem characterized by extremely low temperatures, short growing seasons, and the absence of trees. During the Ice Age, the tundra expanded significantly, covering vast areas of northern Eurasia and North America that are now forested or temperate grasslands. This treeless landscape was dominated by low-growing vegetation, adapted to harsh conditions. The ground was often covered by mosses, lichens, sedges, grasses, and dwarf shrubs like willows and birches. These plants have shallow root systems because the ground beneath them often remains frozen, preventing deeper penetration. Their growth cycles are compressed into the brief summer months when temperatures rise just above freezing and the surface layer of the soil thaws. The low stature of the vegetation is an adaptation to strong winds and prevents heat loss in cold conditions. The climate of these cold deserts was marked by long, intensely cold winters and short, cool summers. Precipitation was generally low, often falling as snow, but the cold temperatures meant that evaporation was also low, so what little moisture fell tended to persist. Strong, persistent winds were a common feature, sweeping across the open, treeless expanses. These winds contributed to the dry conditions by enhancing evaporation and sublimation of snow and ice, and they also played a role in shaping the landscape by moving vast quantities of fine sediment, creating features like loess deposits. Loess is a fine, yellowish, silty sediment deposited by wind, often accumulating in thick layers far from its source. During the Ice Age, large areas adjacent to ice sheets were sources of abundant fine sediment, which was then carried by winds and deposited as extensive loess plains, particularly in Central Europe, China, and parts of North America. These loess deposits often formed fertile soils after the Ice Age, supporting later agricultural development. The periglacial environment was a zone of intense frost action. The repeated freezing and thawing of water in the soil and rock led to a variety of distinctive landforms. Frost heaving, where ice lenses grow in the soil and push up the ground surface, was common. This process can bring stones to the surface and sort them, leading to the formation of patterned ground. Patterned ground refers to a variety of geometric patterns, such as circles, polygons, and stripes, formed by the repeated freezing and thawing of the active layer above permafrost. These patterns are created as stones, and soil particles are sorted by frost action, with larger stones often migrating to the edges of the polygons or circles, forming sorted nets or circles, while unsorted polygons lack distinct stone borders. Another significant periglacial process was solifluction, which is the slow flow of water-saturated soil down a slope, even very gentle ones. In periglacial regions, the active layer, the surface layer that thaws in summer, becomes saturated with meltwater because the underlying permafrost prevents drainage. This waterlogged soil then slowly creeps downslope over the frozen ground, creating distinctive lobe-shaped features or terraces. This process was widespread during the Ice Age, shaping many slopes in areas adjacent to ice sheets, resulting in a landscape with a unique draped appearance. Pingos are another striking feature of periglacial landscapes. These are ice-cored hills that can range from a few meters to tens of meters in height. They form when water beneath the surface freezes and expands, pushing up the overlying sediment into a dome shape. There are two main types: open system pingos, which are fed by groundwater, and closed system pingos, which form in drained lake basins where water is trapped and freezes. When the ice core of a pingo melts, the hill collapses, leaving a circular depression often filled with water, known as a pingo scar. The animal life in these cold deserts was specialized and abundant. The vast grasslands and tundra supported large herds of grazing animals, collectively known as megafauna. Woolly mammoths, with their thick fur and layers of fat, were well adapted to the cold, feeding on grasses and sedges. Woolly rhinoceroses, musk oxen, and reindeer, caribou, also thrived in these environments. These large herbivores provided a food source for powerful predators like saber-toothed cats, cave lions, and dire wolves. Smaller animals like Arctic foxes, lemmings, and various birds also inhabited these regions, forming a complex food web. The productivity of these cold grasslands, sometimes referred to as mammoth steppe, was surprisingly high, supporting a biomass of large animals that is difficult to imagine today in similar latitudes. This steppe tundra biome was a unique mixture of grassland and tundra species, capable of sustaining massive herds. The distribution of these cold deserts during the Ice Age was extensive. In Europe, a vast periglacial zone stretched south of the Scandinavian ice sheet, covering much of what is now Germany, Poland, and parts of France and Russia. In North America, a similar zone existed south of the Laurentide ice sheet, extending into the central United States. These areas were characterized by the features described, including patterned ground, solifluction lobes, and extensive loess deposits. The presence of these landscapes indicates the widespread influence of glacial climates even in areas not directly covered by ice, forming a broad transition zone between the ice sheets and more temperate climates further south. Frozen ground, specifically permafrost, is a defining characteristic of cold regions and played a crucial role in shaping landscapes during the prehistoric ice age. Permafrost is ground, including rock or soil, that remains at or below 0 degrees Celsius for at least 2 consecutive years. It is not necessarily covered in visible ice or snow, but the ground itself is frozen solid. This persistent freezing has profound impacts on hydrology, ecology, and the stability of the land surface. During glacial periods, the extent of permafrost was far greater than it is today, influencing vast areas of the Earth's continents that are now free of permanent ground ice. The formation of permafrost is primarily driven by a cold climate, where the mean annual air temperature is consistently below freezing. Over long periods, cold penetrates into the ground, freezing the water within the soil pores and rock fractures. Once frozen, the ground acts as an insulator, making it difficult for warmth to penetrate deeply, thus maintaining its frozen state. The depth of permafrost can vary significantly, from a few meters in marginal zones to over 1,000 meters in extremely cold regions like central Siberia, where it has persisted for hundreds of thousands of years through multiple glacial cycles. The deeper the permafrost, the longer it has remained frozen. There are different types of permafrost based on its spatial continuity. Continuous permafrost exists where the ground is frozen everywhere, with only small, isolated, unfrozen areas called talics, beneath large, deep lakes or active rivers that do not freeze to the bottom. This type is found in the coldest regions, typically where the mean annual air temperature is below -8 degrees Celsius. Discontinuous permafrost occurs in slightly warmer regions, where mean annual air temperatures range from 0 to -8 degrees Celsius. Here, patches of unfrozen ground, or talics, are common, existing beneath lakes, rivers, or in areas with thicker snow cover or dense vegetation that insulates the ground. Sporadic permafrost is found at the warmest margins of the permafrost zone, where frozen patches are small and widely scattered, existing as isolated islands of frozen ground. During the Ice Age, the continuous and discontinuous permafrost zones were much more extensive, reaching much further south than their present-day limits. A key concept associated with permafrost is the active layer. This is the uppermost layer of ground that thaws in the summer and refreezes in the winter. Its thickness varies depending on temperature, vegetation cover, soil type, and moisture content, typically ranging from a few tens of centimeters to a few meters. The dynamic processes within the active layer, particularly the repeated freezing and thawing, are responsible for many of the distinctive landforms found in permafrost regions. Below the active layer lies the permafrost table, the upper boundary of the perennially frozen ground, which fluctuates slightly with seasonal temperature changes but always remains frozen. Ground ice is a crucial component of permafrost and comes in various forms. Pore ice fills the spaces between soil particles. Segregated ice forms as discrete lenses or layers within the soil, growing as water migrates towards the freezing front, often leading to frost heaving. Massive ice refers to large, solid bodies of ice within the permafrost that are not simply filling pore spaces. These can be remnants of buried glaciers or large ice wedges. Ice wedges are common features, forming when the ground cracks due to extreme cold in winter, a process known as thermal contraction cracking. Meltwater then fills these cracks in spring and freezes, expanding the crack. Over many years, repeated cracking and freezing build up vertical wedge-shaped bodies of ice that can be several meters wide at the top and tens of meters deep. When viewed from above, the polygonal patterns formed by networks of ice wedges define the landscape. The presence of permafrost and ground ice leads to a unique set of geomorphic processes and landforms. Frost heaving, as mentioned, is the upward displacement of soil and rocks due to the growth of ice lenses. This process can sort materials, leading to the formation of patterned ground, such as stone circles, polygons, and stripes, which are visible on the surface. These patterns are created as stones are pushed to the edges of freezing cells, while finer materials remain in the center, a process called cryoturbation or frost churning. Thermokarst is another important process in permafrost regions, involving the subsidence or collapse of the ground surface due to the thawing of ice-rich permafrost. When ground ice melts, the volume of the ground decreases, leading to depressions, hummocks, and irregular terrain. Thermokarst lakes are common, forming in these depressions where meltwater collects. Over time, these lakes can expand as the surrounding permafrost thaws, and they can also drain if their permafrost banks are breached. The formation of thermokarst features was widespread during periods of climate warming at the end of the Ice Age, as vast areas of ice-rich permafrost began to thaw, dramatically altering surface topography. Pingos, the ice-cored hills, are also direct results of permafrost conditions. These distinctive conical mounds can reach heights of over 50 metres and diameters of several hundred metres. Their formation involves the upward injection of water under pressure, which then freezes and expands, pushing up the overlying sediments. The two types, open system and closed system, reflect different hydrological conditions, but both require a permafrost environment for their development and stability. During the Ice Age, the extensive permafrost acted as an impermeable barrier to water drainage. When the active layer thawed in summer, the meltwater could not drain downwards into the frozen ground, leading to widespread waterlogging and the formation of numerous shallow lakes and bogs across the landscape. This poor drainage, combined with low evaporation rates due to cold temperatures, contributed to the characteristic wetness of the active layer in many periglacial areas, despite overall low precipitation. During the Prehistoric Ice Age, a profound transformation occurred across the Earth's surface. Global sea levels dropped dramatically. This was not a minor change, but a monumental shift, with ocean levels falling by as much as 120 to 135 metres below their present-day positions during the peak cold periods, known as glacial maxima. This immense reduction in ocean volume was a direct consequence of vast quantities of water being locked away in colossal ice sheets that accumulated on the continents. The Earth's climate naturally fluctuates between colder glacial periods and warmer interglacial periods. During a glacial period, global temperatures fall, leading to increased snowfall in high latitudes and high altitudes. This snow, instead of melting entirely in the summer, accumulates year after year, compacting under its own weight to form glacial ice. Over tens of thousands of years, these accumulations grow into enormous continental ice sheets, sometimes kilometers thick, covering vast areas of North America, Europe, and Asia. The Laurentide ice sheet in North America and the Scandinavian ice sheet in Europe are prime examples of such immense ice masses. The water that formed these ice sheets originated primarily from the oceans. As water evaporated from the sea surface, it was transported by winds as atmospheric moisture. When this moisture reached colder continental regions, it fell as snow. Because temperatures were low enough, this snow did not return to the oceans as liquid water via rivers or direct melting. Instead, it was sequestered on land in solid form. This continuous transfer of water from the liquid state in the oceans to the solid state on land directly reduced the total volume of water in the global ocean basins. It was a massive hydrological imbalance on a planetary scale. The magnitude of this sea level drop can be difficult to grasp. Imagine emptying a significant portion of all the world's bathtubs into a giant freezer. The exposed land was not just a narrow strip along the coast. It was the vast, gently sloping areas of the continental shelves, which are normally submerged under relatively shallow water. These shelves, which extend outwards from the continents before plunging into the deep ocean, became dry land. For instance, the Bering Strait, a shallow body of water separating Asia and North America today, became a broad land bridge. Similarly, large parts of the North Sea between Great Britain and mainland Europe and vast areas of Southeast Asia's continental shelf were exposed. Scientists have gathered substantial evidence to confirm these past lower sea levels. One key line of evidence comes from submerged coastlines and river valleys. Divers and submersibles have discovered ancient shorelines, beach deposits, and even the remnants of river channels and deltas far below current sea level on the continental shelves. These features could only have formed when those areas were exposed to the atmosphere. Archaeological sites, including tools and settlements of early humans, have also been found on these submerged shelves, indicating that people once lived on land that is now underwater. Another important piece of evidence comes from coral reefs. Corals are marine organisms that build their stony structures in shallow, sunlit waters. The discovery of fossil coral reefs at depths of 100 metres or more below current sea level provides clear proof that the sea surface was once much lower. As sea levels rose after the Ice Age, these corals were drowned and died, but their structures remain as markers of past ocean depths. Furthermore, the study of oxygen isotopes in marine sediments and ice cores provides a powerful proxy for global ice volume and, by extension, sea level. Water molecules contain different isotopes of oxygen, primarily oxygen-16, lighter, and oxygen-18, heavier. During colder periods, when large ice sheets form, water molecules containing the lighter oxygen-16 evaporate more readily from the ocean surface and are preferentially locked up in the continental ice. This leaves the remaining ocean water enriched in the heavier oxygen-18. By analysing the ratio of oxygen-18 to oxygen-16 in the shells of ancient marine organisms, which incorporate the isotopes from the surrounding seawater, or in layers of ice cores, scientists can reconstruct past changes in global ice volume and infer corresponding changes in sea level. A higher oxygen-18 to oxygen-16 ratio in marine sediments indicates a larger global ice volume and thus lower sea levels. The impact of this sea level drop was profound and multifaceted. The exposure of continental shelves created vast new land areas, fundamentally altering the geography of the planet. These newly emerged lands connected continents that are now separated by shallow seas, leading directly to the formation of crucial land bridges. These connections facilitated the migration of animals and, significantly, the dispersal of early human populations across continents, enabling the peopling of previously uninhabited landmasses. Beyond land bridges, the altered coastlines and bathymetry, underwater topography, could have influenced ocean circulation patterns, potentially affecting global climate. The marine ecosystems themselves were profoundly changed, with shifting habitats, increased salinity in some semi-enclosed basins due to reduced water exchange, and alterations in nutrient distribution as coastal zones became dry land. Rivers extended their courses across the newly exposed shelves, carving deeper canyons that are now submerged, forming relic features on the seafloor. Islands that are now isolated were often connected to mainlands or to each other, allowing for greater genetic exchange among populations. As the Earth's climate began to warm at the end of the Ice Age, the immense ice sheets started to melt. This meltwater flowed back into the oceans, causing global sea levels to rise again, a process known as eustatic sea level rise. This rise was often rapid, sometimes occurring at rates of several centimetres per year, leading to the rapid submergence of the land bridges and the vast coastal plains that had been exposed for millennia. This cycle of sea level fall and rise is a fundamental aspect of Earth's glacial interglacial history, leaving an indelible mark on both terrestrial and marine environments. The dramatic drop in global sea levels during the prehistoric ice age led to one of the most significant geographical phenomena of that era: the formation of land bridges. These were strips of land that emerged from beneath shallow seas, connecting continents or islands that are now separated by water. These connections served as vital corridors, allowing the movement and dispersal of animals, plants, and, crucially, early human populations across vast distances. The appearance and disappearance of these land bridges profoundly influenced the distribution of life on Earth. A land bridge is essentially an exposed continental shelf that acts as a continuous land pathway. During glacial maxima, when immense volumes of water were locked up in continental ice sheets, the global sea level plummeted by over 100 metres. This exposed the relatively shallow continental shelves, transforming what were once marine barriers into terrestrial routes. When the climate warmed and the ice sheets melted, the sea levels rose again, submerging these land bridges and isolating the land masses once more. This cyclical process of connection and disconnection had far-reaching evolutionary and historical consequences. One of the most famous and critically important land bridges was Beringia. This vast landmass connected Siberia in Asia with Alaska in North America across what is now the Bering Strait. Beringia was not a narrow strip but a wide expanse, sometimes over 1,000 kilometres wide from north to south. It was exposed multiple times during various glacial periods, but its most continuous and significant exposure occurred from roughly 50,000 years ago until about 11,000 years ago, with the most critical period for human migration being between 25,000 and 11,000 years ago. Despite its high latitude, Beringia itself was largely unglaciated because the cold, dry climate resulted in low snowfall, insufficient to form extensive ice sheets. Instead, it was a vast, treeless steppe tundra environment, supporting a rich ecosystem of hardy grasses, sedges and forbs. This environment was capable of sustaining large populations of Ice Age megafauna, including woolly mammoths, steppe bison, horses and reindeer. Beringia's significance lies primarily in its role as the gateway for the first human populations to enter the Americas. Ancestors of Native Americans are believed to have migrated from Asia into North America across Beringia. While the exact timing and routes are still debated, archaeological evidence suggests multiple waves of migration. Some theories propose that humans moved south through an ice-free corridor that opened up between the Laurentide and Cordilleran ice sheets in western North America. Other theories suggest a coastal migration route, where early peoples used boats to travel along the Pacific coast, even when inland ice sheets blocked terrestrial passage. Regardless of the precise path, Beringia was the essential initial link. Another crucial land bridge system was Sunda Land, located in Southeast Asia. During glacial periods, the shallow waters of the South China Sea and the Java Sea receded, connecting the Malay Peninsula, Sumatra, Borneo, Java, and many smaller islands to the Asian mainland. This created a single, vast landmass that allowed the free dispersal of Asian flora and fauna throughout what is now the Indonesian archipelago. This connection was vital for the migration of various animal species, including tigers, elephants, and rhinoceroses, into regions that are now islands. For early humans, Sundaland provided an extensive land route for their expansion across Southeast Asia, facilitating their journey towards the eastern edges of the continent. Further to the east, the land bridge of Sahul connected Australia, New Guinea and Tasmania. Unlike Sundaland, Sahul was separated from Sundaland by a deep water trench known as the Wallace Line, which remained submerged even at glacial maximum. This deep water barrier meant that the migration of animals and humans from Sundaland to Sahul required significant sea crossings. However, within Sahul itself, the land bridge allowed for the free movement of unique Australian fauna and the early human populations who were the ancestors of Aboriginal Australians and Papuans. The earliest evidence of human presence in Sahul dates back at least 65,000 years, indicating that these early mariners were capable of impressive feats of navigation to cross the water gaps. In Europe, Doggerland was a significant land bridge that connected Great Britain to mainland Europe, specifically to what is now the Netherlands and Denmark, across the southern North Sea. This land bridge was exposed during the last glacial maximum and subsequent warming periods, forming a vast, low-lying land area. Its environment varied, ranging from tundra during the coldest periods to temperate forests and wetlands as the climate warmed. Doggerland was inhabited by various animal species and by Mesolithic human populations, who hunted and fished in its rich ecosystems. As sea levels rose rapidly at the end of the last ice age, Doggerland was gradually submerged, a process that continued until around 8,000 years ago, transforming Britain into an island. Archaeological discoveries, including tools and animal remains dredged from the North Sea, provide direct evidence of this lost land. The general impact of these land bridges was profound. They facilitated extensive faunal exchange between continents. For example, horses and camels, which originated in North America, migrated to Asia via Beringia, while species like woolly mammoths and bison moved from Asia to North America. This mixing of faunas led to new ecological interactions and evolutionary pressures. For human migration, land bridges were instrumental in the peopling of continents, enabling the global spread of Homo sapiens. These connections allowed for genetic flow between geographically separated populations, contributing to the genetic diversity observed in present-day human populations. Conversely, the submergence of these land bridges as the Ice Age ended and sea levels rose led to the isolation of populations. This isolation could result in the evolution of distinct species, or, in some cases, the extinction of isolated groups that could not adapt to new environmental conditions or compete with newly introduced species. The rise of sea levels at the end of the last ice age fundamentally reshaped global geography, creating the continental and island configurations we recognize today, and leaving the land bridges as submerged remnants of a colder, more connected world. The prehistoric ice age presented an extremely challenging environment for plant life. Vast continental ice sheets covered significant portions of the northern continents, and even beyond these glaciated areas, the climate was characterized by brutally cold temperatures, short growing seasons, strong winds, and often dry conditions. Despite these harsh realities, a diverse array of tough plants not only survived but thrived, forming unique ecosystems adapted to the glacial world. Understanding these plants requires examining the specific environmental challenges they faced and the remarkable adaptations they developed. One of the primary challenges for plants was the consistently low temperatures. Prolonged periods below freezing can damage plant tissues by forming ice crystals within cells, leading to dehydration and cell death. The ground itself was often frozen for most of the year, in the form of permafrost, which meant that only a shallow surface layer, the active layer, thawed during the brief summer. This limited the depth to which roots could grow, restricting access to water and nutrients. The growing season was exceptionally short, sometimes only a few weeks to a couple of months long. This meant that plants had to complete their entire life cycle, germination, growth, flowering, and seed production, in a very compressed time frame. Furthermore, the angle of the sun at high latitudes, even in summer, was low, providing less intense solar energy for photosynthesis. Strong, persistent winds swept across the treeless landscapes, leading to desiccation, drying out, of plant tissues and physical damage. While some areas received moderate snowfall, overall precipitation could be low, and the moisture that did fall was often locked up as ice or snow, making it unavailable to plants for much of the year, contributing to cold desert conditions. Soils were often thin, poorly developed, and frequently disturbed by frost action, making nutrient uptake difficult. To overcome these formidable challenges, Ice Age plants developed a range of remarkable adaptations. A common strategy was dwarf growth forms. Many plants, such as dwarf willows and dwarf birches, grew very low to the ground, often only a few centimetres high. This low stature allowed them to remain insulated beneath a protective blanket of snow during the harsh winter months, shielding them from the most extreme winds and temperatures. It also enabled them to absorb heat from the ground more effectively during the short summer. Many of the dominant plant types were evergreens, even among non-coniferous species, or those that could photosynthesize at very low temperatures. Mosses and lichens, for example, are evergreen and can begin photosynthesis immediately when temperatures rise above freezing, without needing to grow new leaves. Some dwarf shrubs also retained their leaves through winter. This allowed them to maximize the limited growing season. Plants also evolved rapid life cycles, completing their growth and reproduction quickly. Many were perennials, meaning they lived for multiple years, storing energy in underground roots or rhizomes to survive the winter and quickly sprout new growth in spring. Vegetative reproduction, such as spreading by rhizomes, stolons or bulbs, was also crucial, as it did not rely on the often unreliable process of seed germination in cold soils. Physiological adaptations to frost hardiness were also essential. Plants developed mechanisms to tolerate freezing, such as accumulating sugars or producing specialized proteins that act as natural antifreezes, preventing ice crystal formation within their cells. Features like hairiness on leaves or waxy cuticles helped reduce water loss through transpiration in windy and dry conditions. The dominant plant types formed distinct biomes. The most widespread was the tundra, characterized by its treeless nature. This biome was dominated by hardy, low-growing plants such as mosses, e.g. sphagnum peat moss, lichens like Cladonia rangiferina or reindeer lichen, sedges, carex species, and various grasses, poa species. Dwarf shrubs, including Arctic willow, Salix arctica, and dwarf birch, Betula nana, were also common. These plants formed a dense low mat over the ground. A particularly unique and productive biome of the Ice Age was the steppe tundra, often referred to as the mammoth steppe. This was not a modern tundra, but a highly productive grassland-like environment that covered vast areas of northern Eurasia and Beringia. It was characterized by a rich mix of grasses, sedges, and nutrient-rich forbs, non-woody flowering plants, with scattered dwarf shrubs. This biome was far more productive than modern tundra, and supported the immense herds of Ice Age megafauna, such as woolly mammoths, woolly rhinoceroses, and steppe bison. The high productivity was likely due to a combination of factors, including cold but relatively dry conditions preventing deep snow cover, which allowed for year-round grazing and high light levels during the long summer days. Further south, or in more sheltered areas, the boreal forest taiga biome, dominated by coniferous trees like spruce, picea, fir, abies, and pine, pinus, was pushed to lower latitudes than its present distribution. These trees are adapted to cold climates and nutrient-poor, often acidic soils, with needle-like leaves that reduce water loss and shed snow easily. In glacial forelands, the areas recently exposed by retreating ice, pioneer species would colonize the raw, newly available land, including early successional grasses, mosses, and lichens, gradually preparing the ground for more complex vegetation. The distribution of these plant zones shifted dramatically with the advance and retreat of ice sheets. During glacial periods, the tree line, the northern limit of tree growth, moved significantly southwards, replacing what are now temperate forests with tundra and steppe tundra. During warmer interglacial periods, the tree line advanced northwards again. Scientists reconstruct these past vegetation patterns primarily through pollen analysis from lake sediments and peat bogs. Pollen grains, being highly resistant to decay, are preserved in these layers, and their types and abundances indicate the dominant plant species present at different times. Macrofossils such as seeds, leaves, and wood fragments, preserved in permafrost or glacial sediments, also provide direct evidence of past plant life. These tough plants were the foundation of the Ice Age terrestrial ecosystems, demonstrating remarkable resilience and adaptability to one of the Earth's most challenging climates. During the Prehistoric Ice Age, the Earth's climate underwent profound shifts, leading to dramatic transformations in global vegetation patterns. One of the most significant changes was the widespread retreat and alteration of forests. As temperatures dropped and vast ice sheets expanded across continents, the conditions became increasingly inhospitable for many tree species, forcing them to either adapt, migrate, or face extinction. This resulted in a landscape where dense forests, once common in many regions, were replaced by more open environments, primarily expansive grasslands and cold, treeless tundra. The primary driver of these forest changes was the severe cooling of the global climate. Average temperatures plummeted, particularly in higher latitudes, making it impossible for many temperate and even some boreal forest species to survive. Trees are highly sensitive to temperature and the length of the growing season. With shorter, cooler summers and longer, harsher winters, the metabolic processes essential for tree growth, such as photosynthesis, were severely limited. Frost damage became a constant threat, and the ground often remained frozen for much of the year, preventing deep root penetration and water uptake. Beyond temperature, changes in moisture availability also played a crucial role. While some areas might have experienced increased snowfall, much of the Earth's water was locked up in the massive ice sheets, leading to a global drop in sea levels and often drier continental interiors. This increased aridity, combined with strong, persistent winds, created conditions that were particularly challenging for forest establishment and survival. Trees require consistent access to liquid water, and frozen ground or insufficient precipitation could lead to physiological drought, even if ice was abundant elsewhere. As conditions deteriorated, forests did not simply vanish, they migrated. Tree species, over many generations, slowly shifted their ranges towards the equator, seeking warmer and more hospitable climates. This migration was a slow process, limited by the dispersal rates of seeds and the rate at which new suitable habitats became available. For example, broadleaf deciduous forests, which are characteristic of temperate climates today, retreated significantly southward in Europe and North America, often surviving in isolated pockets or refugia in southern regions where the climate remained mild enough. Coniferous forests composed of trees like pines, spruces and firs are generally more cold-tolerant than deciduous forests. However, even these boreal species face challenges. While they could extend further north than broadleaf trees, their northern limits were still defined by the extreme cold and the presence of continuous permafrost, which prevented deep rooting. In many areas that are now covered by boreal forests, Ice Age conditions supported only scattered, stunted trees or gave way entirely to other vegetation types. The retreat of forests opened up vast new areas for the expansion of other biomes. The most prominent of these was the tundra, This treeless landscape, characterized by low-growing vegetation such as mosses, lichens, sedges and dwarf shrubs, became widespread in the northern latitudes, bordering the immense ice sheets. Tundra plants are adapted to short-growing seasons, cold temperatures, and often waterlogged soils above permafrost. They grow close to the ground to avoid strong winds and benefit from the insulating properties of snow cover. Another significant biome that expanded during the Ice Age was the mammoth steppe, or steppe tundra. This was a unique and highly productive grassland ecosystem that covered vast areas of northern Eurasia and parts of North America. Unlike modern tundras, which are often wet and boggy, the mammoth steppe was characterized by cold, dry conditions and supported a rich diversity of cold-adapted grasses, sedges and herbaceous plants. This biome was crucial for sustaining the large herds of Ice Age megafauna such as woolly mammoths, woolly rhinoceroses and horses. The productivity of this steppe was likely maintained by the grazing and trampling of these large herbivores, which helped to prevent the growth of woody vegetation and recycle nutrients. The evidence for these dramatic forest changes comes from various scientific disciplines. Palynology, the study of fossil pollen, is a key tool. Scientists extract pollen grains from lake sediments, peat bogs, and ice cores, which can be identified to genus or species level. By analysing changes in pollen assemblages through different layers, researchers can reconstruct past vegetation types and track the migration of forest boundaries over thousands of years. Macrofossil remains, such as preserved wood, leaves, and seeds found in permafrost or ancient lake beds, also provide direct evidence of past plant communities. Furthermore, the distribution of animal fossils can indirectly indicate vegetation, as different animals are associated with specific habitats. For instance, the widespread presence of grazing megafauna supports the idea of extensive grasslands. The changes were not static. As the Ice Age progressed through various glacial and interglacial cycles, forest boundaries shifted back and forth. During warmer interglacial periods, forests would expand again into higher latitudes, only to retreat during subsequent cold glacial maxima. This dynamic interplay between climate and vegetation shaped the ecological history of continents. The fragmentation of forest habitats during glacial periods could also lead to genetic isolation, and, in some cases, localized extinctions of certain tree populations, impacting overall biodiversity. The Prehistoric Ice Age was a time when many of Earth's land surfaces were dominated by immense animals, collectively known as megafauna. This term generally refers to very large animals, typically those weighing over 44 kilograms, 100 pounds, for mammals, or simply animals that were significantly larger than their modern relatives. These colossal creatures were a defining characteristic of the Ice Age ecosystems, particularly in the vast, cold grasslands and tundra environments that replaced many forests. Their impressive size was not merely a coincidence, but a suite of adaptations that allowed them to thrive in the challenging conditions of a glacial world. Some of the most iconic examples of Ice Age megafauna include the woolly mammoth, a shaggy-haired relative of modern elephants, the mastodon, another elephant-like creature with different teeth adapted for browsing, the woolly rhinoceros, a large horned mammal covered in thick fur, and the giant ground sloth, an enormous slow-moving herbivore that could stand on its hind legs. Predators were also part of this megafauna, such as the saber-toothed cat, with its distinctive elongated canine teeth, the cave lion, a larger cousin of today's African lion, and the dire wolf, a robust and powerful canid. Even deer-like animals were larger, exemplified by the Irish elk, which possessed antlers spanning up to 3.5 meters. The primary reason for the large size of many Ice Age animals is often explained by Bergmann's rule. This ecological principle states that within a broadly distributed taxonomic clade, populations and species of larger size are found in colder environments, and species of smaller size are found in warmer regions. The physiological basis for this rule is that larger bodies have a smaller surface area to volume ratio compared to smaller bodies. This means that larger animals lose heat more slowly to their surroundings and can retain body heat more efficiently in cold climates. For an animal living in an environment where temperatures frequently dropped far below freezing, conserving body heat was a critical survival strategy. A large body mass provided a natural thermal buffer against the extreme cold. Beyond heat retention, large size offered several other ecological advantages in the Ice Age environment. For herbivores, a large body allows for a larger digestive system, which can process greater quantities of low-quality forage, such as tough grasses and sedges, more efficiently. In the cold, dry conditions of the mammoth steppe, where nutrient-rich plants might have been scarce or seasonal, the ability to consume and extract energy from abundant but less nutritious vegetation was a significant benefit. Large animals also have greater energy reserves in the form of fat, which could be crucial for surviving long, lean winters when food was scarce or covered by deep snow. For both herbivores and carnivores, large size could also confer advantages in terms of predator defense or hunting efficiency. A massive woolly mammoth was a formidable opponent for any predator, and its sheer size offered protection against attacks. Similarly, large predators like the saber-toothed cat or dire wolf were equipped to take down the enormous herbivores that constituted their prey base. Their size provided the strength and power necessary for subduing such large and dangerous animals. Social behaviour also played a role. Many large Ice Age herbivores like mammoths lived in herds, similar to modern elephants. Living in a group provided collective defence against predators and facilitated foraging by allowing animals to share information about food sources. The larger size of individuals within these herds would have enhanced the overall protective capabilities of the group. Furthermore, large animals tend to have slower reproductive rates, with longer gestation periods and fewer offspring per birth, but their offspring are typically more developed and robust at birth. While this might seem like a disadvantage, it can be a successful strategy in stable environments where adult survival rates are high, as it invests more resources into each offspring, increasing its chances of survival in a harsh world. Other adaptations beyond sheer size also contributed to the survival of megafauna. Many possessed thick layers of insulating fat beneath their skin, providing an additional thermal barrier. Dense, shaggy fur coats, like those seen on woolly mammoths and rhinoceroses, trapped air close to the body, further reducing heat loss. Smaller extremities, such as the ears and tails of mammoths compared to modern elephants, minimized surface area exposed to the cold, further reducing heat dissipation. Specialized teeth for grinding tough, abrasive grasses were also common among the herbivores. The distribution of Ice Age megafauna was widespread across the northern continents, particularly in the vast grasslands and steppe tundra biomes of Eurasia and North America. These open environments provided the extensive grazing grounds necessary to support large populations of these enormous herbivores. The presence of these giant animals fundamentally shaped the ecosystems they inhabited, acting as ecosystem engineers through their grazing, trampling and nutrient cycling, which helped to maintain the open, treeless nature of the mammoth steppe. The woolly mammoth, Mammuthus primigenius, stands as one of the most iconic and thoroughly studied animals of the prehistoric Ice Age. These magnificent creatures, closely related to modern elephants, roamed vast expanses of the northern hemisphere for hundreds of thousands of years, adapting remarkably to the frigid conditions of the Pleistocene epoch. Our understanding of their life comes from a rich fossil record, including bones, teeth, tusks, and uniquely, remarkably preserved frozen carcasses found in the permafrost of Siberia and Alaska, which offer insights into their appearance, diet, and physiology. In terms of appearance, woolly mammoths were similar in size to modern African elephants, standing up to 3.5 meters, 11 feet, tall at the shoulder, but they were more robust and stocky in build. Their most striking feature was their dense, shaggy coat of fur, which could be dark brown, reddish-brown, or even black. This coat consisted of a thick outer layer of long-guard hairs, sometimes reaching 1 meter, 3 feet, in length, overlying a dense insulating undercoat. This double layer of fur provided exceptional insulation against the biting cold and strong winds. Another distinctive feature was their enormous spirally curved tusks. These tusks, which were elongated in sizes, could grow to impressive lengths, sometimes exceeding 5 meters, 16 feet, in older males. The tusks were not merely for show. Evidence suggests they were multi-purpose tools. Mammoths likely used them to dig through snow and ice to access buried vegetation, to strip bark from trees, for defense against predators like saber-toothed cats and dire wolves, and possibly for display or fighting among males during mating season. The wear patterns on fossil tusks provide clues to these behaviours. Further adaptations to the cold included smaller ears and a shorter tail compared to modern elephants. This reduction in surface area minimised heat loss from these extremities, which are typically well vascularised. A prominent hump of fat and muscle on their backs served as an energy reserve, crucial for surviving periods of food scarcity during long winters. Their feet were also adapted, being broad and padded, likely to distribute their weight over snow and soft ground, and possibly equipped with rough soles for better grip on icy surfaces. Woolly mammoths were herbivores, primarily grazers, meaning their diet consisted mainly of grasses, sedges, and other herbaceous plants. Analysis of stomach contents from frozen mammoths has revealed a diet rich in these fibrous plants, along with some dwarf shrubs and mosses. Their molars were specialised for grinding tough vegetation, featuring numerous enamel ridges that provided an efficient grinding surface. They would have spent a significant portion of their day foraging to consume the vast quantities of food required to sustain their large bodies. During winter, they would use their tusks and trunks to sweep away snow to reach the vegetation beneath. Their social behaviour is believed to have been similar to that of modern elephants. Woolly mammoths likely lived in matriarchal herds, led by an older female consisting of females and their young. Adult males might have lived solitary lives or in smaller bachelor groups, joining the female herds only for breeding. This herd structure provided collective defence against predators and facilitated the sharing of knowledge about foraging grounds and migration routes. Mammoths were migratory animals, moving across vast landscapes in search of food and water, following seasonal changes in vegetation availability. Their movements would have been slow but persistent, covering hundreds or even thousands of kilometres over the course of a year. Their large size and adaptations allowed them to traverse diverse and challenging terrains, including snow-covered plains and frozen river valleys. Reproduction in woolly mammoths was likely slow, mirroring that of modern elephants. They had a long gestation period, probably around 22 months, resulting in the birth of a single, relatively large and well-developed calf. Calves would have been dependent on their mothers and the herd for several years, learning essential survival skills. Their slow reproductive rate made them vulnerable to environmental changes and increased predation pressures. The lifespan of a woolly mammoth is estimated to have been similar to that of modern elephants, ranging from 60 to 70 years. Scientists can determine age by studying growth rings in their tusks, much like tree rings, and by examining the wear on their molars. Woolly mammoths played a crucial role in the Ice Age ecosystems, particularly in the mammoth steppe biome. As large grazers, they acted as ecosystem engineers, influencing vegetation structure by consuming vast amounts of plant material, trampling shrubs, and disturbing the soil. Their grazing helped to maintain the open, treeless nature of the steppe, preventing the encroachment of woody plants and facilitating the growth of the grasses and sedges that form the base of the food web. Their dung would have also contributed to nutrient cycling in these environments. The remarkable preservation of woolly mammoth carcasses in permafrost has provided unprecedented detail about their biology. These frozen remains, sometimes complete with skin, hair, muscles, and even internal organs and stomach contents, have allowed scientists to study their diet, genetics, and the specific adaptations that enabled them to survive in an icebound world. DNA extracted from these remains has further clarified their evolutionary history and relationships with modern elephants. The woolly mammoth remains a powerful symbol of the Ice Age, a testament to the incredible adaptability of life in extreme environments. The term saber-toothed cat refers not to a single species, but to several extinct lineages of feliform mammals characterized by unusually long curved canines. Of these, Smilodon fatalis is perhaps the most famous and iconic, a formidable predator that roamed North America during the Ice Age. These were not direct ancestors of modern felines, but rather a distinct, now extinct branch of the cat family, evolving specialized adaptations for hunting large prey. Their existence spanned roughly 2.5 million years, disappearing around 10,000 years ago at the close of the Pleistocene epoch. Smilodon fatalis was a creature of immense power and robust build, significantly more muscular than a modern lion. Standing about 120 centimeters, 47 inches, tall at the shoulder and weighing between 160 and 280 kilograms, 350 to 620 pounds, It possessed an exceptionally stocky body with particularly strong forelimbs. Its hindquarters were slightly lower, giving it a somewhat stooped appearance. The most striking feature, of course, was its dentition. The upper canine teeth could reach up to 28 centimeters, 11 inches, in length, extending well below the lower jaw even when the mouth was closed. These teeth were flattened side to side, giving them a blade-like edge, and while they had microscopic serrations, they were not designed for cutting meat like a steak knife, but rather for piercing and slicing. The lower canines were much smaller and cone-shaped. The skull of Smilodon was uniquely adapted to accommodate these massive canines. Its jaw could open to an astonishing 120 degrees, far wider than any modern cat, allowing it to clear its lower jaw from the path of its elongated upper teeth. However, this wide gape came with a trade-off. The bite force, particularly at the tips of the sabers, was weaker than that of modern big cats. This meant that the sabers were likely fragile and prone to breaking if they struck bone or if the prey struggled violently. The weak bite force relative to its size indicates that Smilodon did not kill its prey by a crushing bite to the windpipe or skull, as modern lions or jaguars do. Instead, its killing strategy relied on precision and the immense strength of its body. Smilodon was not built for sustained chases. Its heavy, muscular build and relatively shorter limbs compared to modern cheetahs or even lions suggest it was an ambush predator. Its immense forelimb musculature indicates it would have wrestled prey to the ground using sheer power. Once the prey was subdued, likely on its side or back, the Smilodon would deliver a precise deep stab to the throat or belly, aiming to sever major blood vessels like the carotid artery or jugular vein, or perhaps the trachea. The flattened sabers would inflict a rapid, debilitating wound, leading to quick blood loss and shock. The strong neck muscles of Smilodon were crucial for delivering this precise strike, allowing it to drive its head downwards with force. This method minimized the risk of breaking the delicate sabers by avoiding contact with bone and reducing the struggle time of the victim. The prey of Smilodon fatalis would have been large, relatively slow-moving herbivores abundant during the Ice Age. Evidence from fossil sites, particularly the La Brea tar pits in California, suggests they primarily hunted animals like bison, camels, camelops, ground sloths, paramylodon, megalonyx, horses, equus, and juvenile mammoths or mastodons. Their specialized teeth were ill-suited for hunting smaller, agile prey, which could easily escape the deep but slow thrust of the sabers. Nor were they designed for crushing bones, meaning they would have left significant portions of a carcass to other scavengers. The sheer number of Smilodon fossils found at La Brea, often with healed injuries, points towards a perilous lifestyle and perhaps communal hunting. The abundance of Smilodon fossils at the La Brea tar pits, estimated at tens of thousands of individuals, provides unparalleled insight into their lives. Many of these fossils show evidence of severe injuries, including broken bones that had healed, suggesting that individuals survived serious wounds. This prevalence of healed injuries is often interpreted as evidence of social behaviour. If a Smilodon was injured and unable to hunt effectively, it likely would have starved if it were solitary. However, if it was part of a group, it could have been supported by other members, sharing kills until it recovered. This cooperation would have been highly advantageous for hunting very large and dangerous prey, as well as for competing with other formidable predators of the Ice Age, such as American lions, Panthera atrox, dire wolves, Inocionderus, and short-faced bears, Arctodus simus. As an apex predator, Smilodon fatalis occupied a critical niche in the Ice Age ecosystem of North and South America. They played a significant role in controlling the populations of large herbivores, ensuring a balance within the food web. Their geographic range extended from what is now southern Canada through the United States and down into parts of South America. There were actually 3 recognized species of Smilodon: Smilodon gracilis, the earliest and smallest, Smilodon fatalis, the well-known North American species, and Smilodon populator, the largest species found exclusively in South America, which was even bigger and more robust than its North American cousin. The extinction of Smilodon occurred abruptly around 10,000 years ago, coinciding with the end of the last glacial period, known as the Younger Dryas. The causes of their disappearance, along with many other megafauna, are still debated but likely involve a combination of factors. Rapid climate change played a significant role. As the ice sheets retreated, the vast grasslands and open steppe environments that supported their large prey began to shrink and were replaced by denser forests and new biomes. The Megaherbivores that Smilodon specialised in hunting, such as mammoths, mastodons, and giant ground sloths, also faced extinction pressures from habitat loss and, increasingly, from human hunting. As their primary food sources diminished, Smilodon's highly specialised hunting strategy became a liability. While direct evidence of humans hunting Smilodon is rare, competition for declining prey resources with expanding human populations and other generalist predators like dire wolves could have contributed to their decline. The specialisation that made them such efficient hunters of large prey ultimately made them vulnerable when those prey populations disappeared, leading to their complete extinction and leaving no modern descendants with comparable dental specializations. The woolly rhinoceros, Chelodonta antiquitatis, was a majestic and iconic megafauna of the Ice Age, a formidable herbivore perfectly adapted to the cold, treeless steppes of Eurasia. Unlike its modern tropical relatives, this rhinoceros was built for survival in intensely frigid environments, a testament to the diverse evolutionary pathways within the rhinoceros family. Its existence spanned from roughly 350,000 years ago until its disappearance around 10,000 years ago, coinciding with the end of the last glacial maximum. Measuring approximately 3.5 to 4 metres, 11 to 13 feet, in length, and standing about 180 centimetres, 71 inches, tall at the shoulder, the woolly rhino was comparable in size to a modern white rhinoceros, weighing between 2 and 3 tons, 4,400 to 6,600 pounds. Its most striking adaptation to the cold was its dense, shaggy coat of reddish-brown fur, composed of long, guard hairs and a thick undercoat, providing excellent insulation against the freezing winds and snow. Evidence for this fur comes from remarkably well-preserved carcasses discovered in the permafrost of Siberia and from ancient cave paintings. For instance, the discovery of a nearly complete juvenile woolly rhino carcass, nicknamed Sasha, in Siberia in 2014 provided direct evidence of its fur colour and texture. Another distinctive feature was a prominent hump on its shoulders, likely a deposit of fat that served as an energy reserve, similar to a camel's hump. This fatty reserve would have been crucial for survival during the long, harsh winters when food was scarce. Its legs were short and stout, providing stability and traction on snowy or icy terrain. Its ears were relatively small, another adaptation to reduce heat loss in the cold. The woolly rhinoceros possessed 2 horns, both made of keratin, the same material as hair and fingernails. The front horn was particularly impressive, often exceeding 1 metre, 3 feet, in length. Unlike the conical horns of modern rhinos, the woolly rhino's front horn was flattened and broad, with grooves along its surface. This unique shape suggests a specialised function beyond defence. Scientists hypothesize that this flattened horn was used as a snowplow, or a tool to sweep aside snow and ice to uncover buried vegetation, or perhaps even for foraging by stripping bark or digging for roots. Its skull was adapted with a bony nasal septum to provide strong support for this large horn. The back horn was smaller and more conical. The diet of the woolly rhino consisted primarily of coarse dry grasses, sedges, and other herbaceous plants typical of the mammoth steppe environment. Its teeth were high-crowned and lacked enamel on the inside of the folds, an adaptation for grinding tough, abrasive vegetation. Analysis of preserved stomach contents and fossilized dung, coprolites, has confirmed its grazing diet. This specialization meant it thrived in open, expansive grasslands and cold steppes, ranging across vast areas of Eurasia, from Western Europe through Siberia to China. They were not typically found in dense forests or wetlands, as these environments did not provide their preferred food sources or suitable terrain. While direct evidence of their social structure is limited, it is generally believed that woolly rhinos, similar to modern black rhinoceroses, were largely solitary animals, or possibly lived in small, loose groups. Their massive size and formidable horns would have provided ample defense against predators such as cave lions, dire wolves, and possibly even humans. However, evidence from archaeological sites suggests that early humans did hunt woolly rhinoceroses, often targeting individuals that may have been isolated, young, or injured. Cave paintings, such as those found in Chauvet Cave in France, depict woolly rhinoceroses with remarkable accuracy, indicating their significant presence in the lives of Ice Age people. The fossil record of Coelodonta antiquitatis is extensive and widespread across Eurasia. Numerous skeletal remains have been unearthed from various sites, providing detailed information about their anatomy. However, the most extraordinary discoveries have been frozen carcasses found in the permafrost of Siberia, particularly in Yakutia. These frozen specimens have provided unique insights into their soft tissues, fur, internal organs, and even the contents of their stomachs, offering a window into their diet and the paleo environment they inhabited. These mummified remains have allowed scientists to study their adaptations to cold in unprecedented detail, including their thick skin and fat layers. The differences between the woolly rhinoceros and modern rhinoceros species are stark and reflect their divergent evolutionary paths. Modern rhinos, such as the white, black Indian, Javan and Sumatran rhinos, are typically found in tropical and subtropical regions of Africa and Asia. They have sparse hair or are largely hairless, and their horns are generally more conical. The woolly rhino's unique adaptations to extreme cold, including its shaggy coat, fat hump, and specialized horn for snow plowing, set it apart as a true Ice Age specialist. The extinction of the woolly rhinoceros occurred around 10,000 years ago, during the rapid warming period at the end of the last Ice Age. Like many other megafauna, its disappearance is attributed primarily to climate change. As temperatures rose, the vast, dry steppe tundra environment that was its preferred habitat began to shrink. Forests and wetlands expanded, replacing the grasslands that provided their specialized diet. This fundamental shift in vegetation and landscape made it increasingly difficult for the woolly rhino to find adequate food. While early human hunting pressure may have been a contributing factor, particularly on already stressed populations, the overwhelming scientific consensus points to the dramatic environmental transformations as the primary cause of its demise. Its specialized adaptations, once key to its survival, became a vulnerability in a rapidly changing world. Giant ground sloths represent an astonishing chapter in the history of megafauna, a diverse group of extinct mammals that inhabited North and South America throughout the Cenozoic era, culminating in the impressive forms of the Ice Age. Unlike their small, arboreal modern relatives that cling to trees, these ancient sloths were massive terrestrial creatures, with some species rivaling the size of elephants. They were an integral part of the Ice Age ecosystems, playing the role of large herbivores. The giant ground sloths comprise several distinct genera, each with its own characteristics, though all shared certain common features of gigantism and adaptation for herbivory. Perhaps the most famous and largest was Megatherium americanum, primarily found in South America. This colossal animal could reach lengths of up to 6 meters, 20 feet, from head to tail, and weighed several tons, often estimated to be between 3 and 4 tons, making it comparable in mass to a modern adult elephant. Its sheer size would have been an imposing sight in the Pleistocene landscapes. Other significant genera include Eromatherium, which ranged into North America, particularly the southeastern United States, and was also of considerable size. Megalonyx, a slightly smaller but still very large sloth, more commonly found across North America, famously studied by Thomas Jefferson, and Glossotherium, another prominent South American genus. Physically, giant sloths possessed a robust, heavily built skeleton. Their bones were dense and thick, designed to support their immense weight. They had large, powerful claws, which, contrary to their modern tree-dwelling cousins, were not primarily for climbing, though juveniles of some species might have been able to, but for digging, defense, and stripping leaves from branches. Their feet were adapted for walking on the sides of their feet to protect these long claws. They lacked incisors and canines, instead possessing a set of peg-like cheek teeth that were continuously growing and well-suited for grinding tough plant material. A notable adaptation of many giant sloths was their ability to stand on their hind legs. They possessed a broad, strong pelvis and a massive muscular tail that acted as a sturdy tripod. This allowed them to rear up to reach higher branches for browse, extending their feeding range. This facultative bipedalism, while not their primary mode of locomotion, would have given them access to vegetation unavailable to other herbivores and provided a formidable defensive posture. Some species, like Megatherium, may have even used their forelimbs with their large claws to pull down tree branches or dig for roots and tubers. Giant ground sloths were herbivores, primarily browsers that fed on leaves, twigs and shrubs. Analysis of coprolites, or fossilized dung, from dry cave sites has provided direct evidence of their diet, confirming a strong preference for specific plant species that were abundant in their respective habitats. For example, coprolites from Mylodon darwini, another South American giant sloth, in Chile's Mylodon cave revealed a diet of grasses, sedges and various shrubs. While overwhelmingly herbivorous, some scientists have theorized that larger sloths might have occasionally supplemented their diet with carrion, but direct evidence for widespread omnivory is limited, and their dental structure strongly indicates a plant-based diet. Some species also possessed osteoderms, small bony plates embedded within their skin, providing an additional layer of protection against predators. Despite their enormous size, ground sloths were likely slow and deliberate in their movements. Their massive bodies and the need to protect their claws meant a lumbering gait when moving quadrupedally. They inhabited a variety of environments across the Americas, adapting to different vegetation types ranging from open grasslands to woodlands and forests. In the ecosystems they inhabited, they played a vital role as major herbivores, influencing plant communities through their extensive browse. Their consumption of large quantities of plant matter and subsequent defecation also likely contributed to seed dispersal, much like large herbivores do today. The social structure of giant sloths is largely inferred from modern analogues and fossil evidence, suggesting they were likely solitary animals or lived in small family groups, as seen with modern sloths. Their primary defense against predators, such as saber-toothed cats, Smilodon, American lions, Panthera atrox, and dire wolves, Enochiondurus, was their immense size, powerful claws and thick hide. They could also deliver formidable blows with their forelimbs. Evidence of direct confrontations with predators is scarce, but it is clear that their bulk made them less vulnerable to predation than smaller animals. The fossil record of giant ground sloths is extensive across both North and South America, with numerous discoveries providing rich insights into their anatomy, distribution, and diet. Beyond skeletal remains, some exceptionally well-preserved mummified remains have been found in arid caves, particularly in South America, offering rare glimpses of their fur, skin, and even soft tissues. These finds, such as those from Cueva del Milodon in Chile, have significantly advanced our understanding of their appearance and physiology. The extinction of the giant ground sloths occurred around 10,000 years ago, part of the broader megafaunal extinction event at the end of the Pleistocene epoch. The causes are widely debated, with the leading theories focusing on climate change, human hunting, or a combination of both. As the Ice Age ended, rapid warming led to significant shifts in vegetation. Many of the plant communities that formed the dietary basis for giant sloths either disappeared or were drastically reduced, posing immense challenges to their survival. Simultaneously, early human populations expanded across the Americas, and there is increasing archaeological evidence suggesting that humans did hunt ground sloths. Cut marks on bones and the presence of sloth remains in human archaeological sites support this. Their slow reproduction rates and specialized diets would have made them particularly vulnerable to both environmental changes and human hunting pressure. The loss of these magnificent giants marked a profound change in the American ecosystems, leaving behind only their much smaller tree-dwelling cousins as their living relatives. The cave bear, scientifically known as Ursus spelaeus, was a formidable inhabitant of Europe and parts of Asia during the Pleistocene epoch, commonly referred to as the Ice Age. This species emerged approximately 300,000 years ago and became extinct around 24,000 years ago. Unlike its modern relatives, the cave bear was an enormous animal, significantly larger and more robust than today's brown bears. Adult males could stand over 3 meters tall on their hind legs and weigh up to 1,000 kilograms, making them one of the largest land mammals of their time. Their sheer size suggests a creature well adapted to the cold and capable of defending itself against other large predators. Physical examination of cave bear fossils reveals distinct characteristics. Their skulls were broad and dome-shaped, with a steep forehead, a feature that sets them apart from the flatter skulls of brown bears. Their teeth, particularly the molars, were remarkably wide and complex, with numerous cusps and a flattened grinding surface. This dental morphology provides crucial evidence about their diet. Their limb bones were thick and heavy, indicating a powerful, stocky build, suitable for navigating varied terrain and supporting their immense weight. While direct evidence of their fur is scarce, it is inferred that they possessed a thick, insulating coat, similar to other Ice Age megafauna, to withstand the frigid glacial and interglacial climates. Despite their imposing size and fearsome appearance, scientific evidence strongly suggests that cave bears were predominantly herbivorous. This contrasts sharply with modern brown bears, which are omnivores with a significant meat component in their diet. The primary evidence for the cave bear's vegetarian diet comes from the analysis of their teeth and bones. The wear patterns on their molars show extensive grinding, consistent with processing tough plant material, rather than the shearing and tearing associated with meat consumption. Furthermore, isotopic analysis of their bone collagen, which examines the ratios of different carbon and nitrogen isotopes, indicates a diet primarily composed of plants. Some studies have even found fossilized plant remains within the dental calculus, hardened plaque, on their teeth, providing direct proof of their plant-based diet. It is believed they consumed a wide variety of vegetation, including grasses, herbs, berries, and roots, depending on seasonal availability. Their large size might have been an adaptation to process large quantities of low-quality plant matter, similar to modern large herbivores. Caves were central to the life cycle of the cave bear, hence their common name. These natural shelters provided essential refuge from the harsh Ice Age climate and protection from predators. Cave bears used caves primarily for hibernation during the long cold winters. During this period, their metabolism would slow down significantly, allowing them to conserve energy. Female cave bears would also give birth to their cubs in the safety of these caves, typically producing 1 to 3 cubs that would remain with their mother for an extended period, learning survival skills before venturing out independently. The vast number of cave bear bones found in specific cave systems across Europe, sometimes numbering in the thousands, indicates that these sites were repeatedly used over many millennia by successive generations of bears. These bone accumulations are not typically the result of human hunting or predation, but rather represent natural mortality within the dens, with bears dying during hibernation or from other natural causes. The sheer density of remains suggests that many individuals would return to the same caves year after year. The geographic distribution of Ursus spelaeus was widespread across Europe, extending from Spain and Great Britain in the west, through Central Europe, to parts of Russia and the Caucasus Mountains in the east. They inhabited a variety of environments, from forested areas to open steppes, as long as suitable caves were available for shelter. Their preference for caves limited their range to regions with karstic limestone formations, which are prone to cave development. Fossil evidence shows they were particularly abundant in areas like the Carpathian Mountains and the Swabian Jura. In terms of social behaviour, it is inferred that cave bears were largely solitary animals, much like most modern bear species, except during mating season or when a female was raising cubs. However, the concentration of so many individuals in the same caves for hibernation suggests a degree of tolerance, if not direct social interaction, within these communal dens. This communal denning behaviour is a unique aspect of their ecology compared to most modern bears, which typically seek out individual dens. The extinction of the cave bear occurred relatively suddenly around 24,000 years ago, coinciding with a period of significant climate change known as the last glacial maximum. Several theories attempt to explain their disappearance. One leading hypothesis points to their highly specialised herbivorous diet. As the climate became colder and drier during the peak of the last glaciation, the availability of their preferred plant foods, particularly soft, non-grassy vegetation, may have declined sharply. This dietary specialisation could have made them vulnerable to environmental shifts that more omnivorous bears, like the brown bear, were able to adapt to. Another contributing factor might have been increased competition with early modern humans for cave resources. While humans did not extensively hunt cave bears, their presence in caves could have disrupted the bears' hibernation cycles or forced them into less suitable dens, impacting their reproductive success and survival. It is likely that a combination of these factors, climate change leading to habitat loss and dietary stress coupled with human presence, ultimately led to the demise of these magnificent Ice Age giants. Their extinction serves as a reminder of how even large, seemingly robust species can be vulnerable to environmental pressures when their ecological niche is highly specialized. The dire wolf, scientifically named Canis dirus, was an iconic predator of the late Pleistocene epoch, or Ice Age, in North America. This powerful canid lived from approximately 250,000 years ago until its extinction around 10,000 years ago. It was one of the most common large carnivores in its ecosystem, playing a crucial role in the food web alongside other formidable predators like saber-toothed cats and American lions. The dire wolf was not simply a larger version of the modern grey wolf. It possessed distinct anatomical features that reflect its specialized predatory lifestyle. In terms of size and appearance, the dire wolf was indeed larger and more robust than any living wolf species. Adult dire wolves typically weighed between 50 and 75 kilograms, with some individuals potentially exceeding 100 kilograms, making them about 25% heavier than the average modern grey wolf. Their build was stockier and more muscular, with a broader skull and more powerful jaws. Their teeth were larger and more robust, particularly their molars, which showed adaptations for crushing bone, suggesting they were capable of consuming more of their prey than modern wolves. Their limbs, while strong, were relatively shorter than those of the grey wolf, indicating a powerful, crushing bite, rather than sustained pursuit over long distances. This suggests they relied on strength and pack cooperation to bring down large prey. The geographic distribution of the dire wolf was primarily concentrated across North America. Fossil evidence indicates their presence from Alaska in the north to Florida in the southeast, and as far south as parts of South America, including Peru and Bolivia, although they were most abundant in what is now the United States. One of the most significant sites for dire wolf fossils is the La Brea tar pits in Los Angeles, California, where thousands of individuals became trapped over tens of thousands of years, providing an unparalleled record of their population structure, diet, and interactions with other Ice Age fauna. Evidence strongly suggests that dire wolves were pack hunters, similar to modern grey wolves, but likely even more reliant on this strategy given the size of their primary prey. Their robust build and powerful jaws were well suited for taking down large herbivores of the Ice Age, such as bison, horses, camels, ground sloths, and possibly even juvenile mammoths or mastodons. The sheer number of dire wolf fossils found together at sites like La Brea, often alongside the remains of large herbivores, supports the idea of cooperative hunting and scavenging. Their ability to crush bone would have allowed them to access marrow, a rich source of nutrients, and process carcasses more thoroughly than some other predators. A direct comparison to the modern grey wolf, Canis lupus, highlights the unique adaptations of the dire wolf. While both were pack-hunting canids, the dire wolf was consistently larger, heavier, and possessed a more robust skeletal structure. Its skull was broader, and its teeth were more massive, particularly the carnassials and molars, indicating a greater capacity for bone crushing. The grey wolf, by contrast, has relatively longer legs and a more gracile build, which is advantageous for long-distance pursuit and endurance running. These anatomical differences suggest a divergence in hunting strategies and ecological niches, with the dire wolf being more specialised for tackling very large, powerful prey, while the grey wolf might have been more versatile in its prey selection and hunting methods. The social structure of dire wolves is inferred to have been complex, similar to modern pack-hunting canids, with established hierarchies and cooperative behaviours essential for successful hunting and raising young. Fossil evidence from La Brea shows individuals of various ages, including juveniles, suggesting that pups were raised within the pack structure. This social complexity would have been vital for survival in an environment teeming with large, dangerous animals and competing predators. Dire wolves were part of a diverse guild of large carnivores in Ice Age North America, including the saber-toothed cat, Smilodon fatalis, the American lion, Panthera atrox, and the short-faced bear, Arctodus simus. These predators likely competed for resources, but also coexisted through niche partitioning. Dire wolves, as cursorial, running pack hunters, would have occupied a different predatory niche than the ambush-hunting saber-toothed cats or the solitary American lions. Scavenging opportunities would also have been a significant part of their diet, particularly from the kills of other large predators or from animals trapped in natural hazards like tar pits. The extinction of the dire wolf occurred at the end of the last ice age, approximately 10,000 years ago, as part of a larger megafaunal extinction event that saw the disappearance of many large animals in North and South America. Several theories attempt to explain their demise. The most prominent hypothesis links their extinction to the disappearance of their primary large prey species, such as horses, camels, and bison, which were severely impacted by rapid climate change and increasing human hunting pressure. As their specialized food source dwindled, the dire wolf, being less adaptable than the more generalized grey wolf, may have struggled to find sufficient food. Competition with the expanding populations of modern humans, who were also skilled hunters, and potentially with the grey wolf, which arrived in North America later and was more adaptable, could have further exacerbated their decline. The dire wolf's reliance on very large prey likely made it vulnerable to the ecological shifts at the close of the Pleistocene, leading to its eventual disappearance from the Earth. The Ice Age, a period spanning hundreds of thousands of years within the Pleistocene epoch, was a time of profound environmental change, characterized by vast ice sheets and dramatically altered landscapes. Amidst these challenging conditions, early humans not only survived but thrived, adapting ingeniously to a world vastly different from our own. The term early humans during this period primarily refers to two significant groups: Homo neanderthalensis, or Neanderthals, and Homo sapiens, or modern humans. Both groups developed remarkable strategies for survival, leaving behind a rich archaeological record of their lives. Neanderthals, Homo neanderthalensis, were a distinct human species that inhabited Europe and parts of Asia from approximately 400,000 years ago until their disappearance around 40,000 years ago. Physically, Neanderthals were robustly built, with strong, heavy bones, wide shoulders, and a barrel chest, adaptations believed to have helped them conserve body heat in cold climates. They possessed prominent brow ridges, a receding forehead, and a large nose, which may have helped warm and humidify cold, dry air before it reached their lungs. Their brain size was, on average, comparable to, or even slightly larger than that of modern humans, indicating considerable cognitive abilities. Neanderthal culture and technology are primarily associated with the Middle Paleolithic period and the Mousterian stone tool industry. Their tools, crafted using a technique called l'évaloir, involved preparing a stone core to produce flakes of a predetermined size and shape, which were then retouched into scrapers, points, and knives. These tools were versatile, used for butchering animals, preparing hides, and working wood. Neanderthals were skilled hunters, primarily targeting large and medium-sized game such as mammoths, woolly rhinoceroses, bison, and reindeer. Evidence suggests they engaged in close-range hunting, requiring significant strength and cooperation. They mastered the use of fire for warmth, cooking, and light, and constructed simple shelters, often at the mouths of caves or in open-air sites, using animal hides and bones. Archaeological findings also indicate that Neanderthals practiced burial of their dead, sometimes with grave goods, suggesting a degree of symbolic thought, and perhaps a belief in an afterlife. They also cared for the sick and elderly, as evidenced by skeletons showing healed injuries that would have required communal support. Homo sapiens, or modern humans, originated in Africa and began their dispersal out of the continent approximately 100,000 to 60,000 years ago, eventually populating every continent. Physically, Homo sapiens were more gracile than Neanderthals, with a lighter skeletal build, a high forehead, and a distinct chin. Their physical adaptations were less specialized for extreme cold, suggesting a greater reliance on cultural adaptations. The arrival of Homo sapiens in Europe marked the beginning of the Upper Paleolithic period, characterized by a significant technological and cultural revolution. Modern humans developed more sophisticated and diverse stone tools, including blade technology, which allowed for the production of long, thin, sharp flakes from a single core, maximizing raw material use. They also innovated with new materials, creating tools from bone, antler, and ivory, such as needles for sewing tailored clothing, harpoons for fishing, and spear throwers, atlatls, that significantly increased the range and power of thrown spears. The development of bows and arrows further enhanced their hunting efficiency, allowing for safer, long-distance kills. Homo sapiens employed diverse and highly effective hunting strategies, often targeting a wider range of prey species than Neanderthals, including smaller animals and fish, in addition to large game. Their advanced tools and cooperative hunting methods allowed them to exploit resources more thoroughly. A hallmark of Upper Paleolithic Homo sapiens is their rich artistic and symbolic expression. This includes the breathtaking cave paintings found in sites like Lascaux and Chauvet in France, depicting animals with remarkable realism and dynamism. They also created portable art such as carved figurines, e.g. Venus figurines, and decorated tools, indicating complex abstract thought, symbolic communication, and possibly ritualistic practices. Elaborate burials, sometimes with intricate grave goods and ochre, further underscore their complex social structures and symbolic worlds. To survive the extreme cold of the Ice Age, Homo sapiens developed sophisticated shelters, including semi-subterranean dwellings made from mammoth bones and hides, providing excellent insulation. Their ability to make tailored clothing, using bone needles to sew animal skins, was a crucial adaptation, allowing them to retain body heat more effectively than simpler draped hides. This technological ingenuity enabled them to expand into the coldest regions of the globe. The migrations of Homo sapiens during the Ice Age were extraordinary. They crossed vast distances, including land bridges exposed by lower sea levels, such as Beringia, which connected Asia and North America, leading to the peopling of the Americas. They also reached Australia by sea, demonstrating advanced navigation skills. Their adaptability allowed them to thrive in a wide array of environments, from Arctic tundras to temperate forests. The period of coexistence between Neanderthals and Homo sapiens in Europe, lasting for several thousand years, is a subject of ongoing research. While the exact nature of their interactions is debated, archaeological and genetic evidence suggests both competition and limited interbreeding occurred. Ultimately, Neanderthals disappeared, and Homo sapiens became the sole surviving human species. The resilience and ingenuity of both Neanderthals and early Homo sapiens in adapting to the harsh and dynamic conditions of the Ice Age underscore the remarkable capacity of human populations to survive and innovate in the face of profound environmental challenges. Their legacy is etched in the archaeological record, providing a window into the lives of our ancient ancestors in a frozen world. Neanderthals, formerly known as Homo neanderthalensis, were a distinct species of archaic humans who inhabited Eurasia for a significant period during the Middle and Late Pleistocene epoch. Their existence spanned from roughly 400,000 years ago to about 40,000 years ago. They were highly adapted to the cold, often harsh, environments of Ice Age Europe and parts of Asia. Understanding their life involves examining their physical characteristics, their cognitive abilities, their sophisticated tool-making and hunting strategies, and their social behaviours. Physically, Neanderthals were robust and powerfully built. They possessed a stocky body, a large rib cage, and strong limbs, features that are interpreted as adaptations to cold climates and a physically demanding lifestyle. Their average height was about 165 centimetres for males and 155 centimetres for females. Their skulls were elongated and low, with prominent brow ridges, a large nose and a receding forehead, but housed a brain size comparable to, or even slightly larger than, that of modern humans, averaging around 1,500 cubic centimetres. This large brain size suggests a high level of cognitive capacity. Their large nasal passages are thought to have helped warm and humidify the cold, dry air before it reached their lungs, another adaptation to their environment. The intelligence of Neanderthals is a topic of ongoing scientific discussion, but archaeological evidence increasingly points to complex cognitive abilities. They were not the brutish, unintelligent beings often depicted in earlier popular culture. Their tool-making skills demonstrate foresight, planning, and a deep understanding of material properties. They developed the Mousterian tool industry, which involved a sophisticated technique called the lever-loir method. This method required preparing a stone core in a specific way before striking off flakes of a predetermined size and shape. This was a complex multi-step process that indicates abstract thought and an ability to visualize the final product before its creation. These tools included scrapers, points, and denticulates, used for a variety of tasks. Neanderthals were skilled hunters, capable of taking down large Ice Age animals. Their primary hunting strategy involved close-quarters combat with prey such as woolly mammoths, woolly rhinoceroses, bison, and reindeer. Evidence from archaeological sites, including bone assemblages with cut marks and impact fractures, suggests they were effective at hunting these formidable animals. The Mysterian points they made were likely hafted onto spears, though whether these were thrusting spears or projectile spears is debated. The high incidence of fractures found in Neanderthal skeletons, similar to those seen in modern rodeo riders, supports the idea of frequent close encounters with large, dangerous animals, suggesting a physically hazardous hunting style. They were not merely scavengers, they were active and proficient predators at the top of their food chain. Their diet was heavily reliant on meat, reflecting the availability of a large game in their cold environments. However, recent studies have also shown that their diet was more varied than previously thought, including plant foods, nuts, and even marine resources in coastal areas. This dietary flexibility demonstrates their ability to exploit diverse food sources available in different ecological niches. The processing of animal hides for clothing and shelter was also essential for survival in the cold. Tools for scraping hides are common in Neanderthal archaeological sites, indicating their proficiency in this vital activity. Neanderthals lived in small dispersed groups, likely extended family units. Evidence suggests they cared for the sick and elderly. Skeletons show healed fractures, and individuals who survived severe injuries or debilitating conditions, indicating that others in the group must have provided care and support. This behaviour points to a strong sense of community and empathy. For example, the Shanidar 1 skeleton, an elderly male, shows evidence of multiple healed injuries, including a crushed eye socket and a withered arm, suggesting he would have been severely incapacitated and dependent on his group for survival. Their use of fire was also fundamental to their survival. Fire provided warmth, light, protection from predators, and a means to cook food, making it more digestible and safer. Control of fire was a critical adaptation to the cold European winters. They likely maintained fires for extended periods, rather than starting new ones frequently, given the difficulty of ignition. While the evidence is less abundant than for modern humans, there are indications of symbolic behaviour among Neanderthals. They used pigments such as ochre, which may have been for body decoration or other symbolic purposes. Some archaeological sites have yielded perforated shells and eagle talons, suggesting they may have created personal ornaments. There is also limited evidence of intentional burial of their dead, sometimes with grave goods like animal bones or tools, which could imply a belief in an afterlife or a form of ritual. However, the interpretation of these symbolic behaviours remains a subject of active research and debate. Neanderthals adapted remarkably well to the fluctuating glacial and interglacial periods of the Ice Age. During cold phases, they thrived in tundra and steppe environments, following herds of large game. During warmer interglacial periods, they adapted to more forested landscapes. Their ability to persist for hundreds of thousands of years across a vast geographic range through significant climate shifts speaks volumes about their resilience and adaptability. The disappearance of Neanderthals around 40,000 years ago, coinciding with the arrival and spread of modern humans, Homo sapiens, into Europe, is one of the most debated topics in human evolution. Various theories have been proposed, including climate change, competition with Homo sapiens for resources, greater technological or social advantages of modern humans, or even interbreeding and assimilation into the larger Homo sapiens population. It is likely that a combination of these factors contributed to their eventual decline. Genetic evidence indicates that Neanderthals and modern humans did interbreed, and many people of Eurasian descent today carry a small percentage of Neanderthal DNA, suggesting that their legacy continues within the modern human gene pool. The study of Neanderthals continues to reveal a complex and fascinating picture of a highly successful human species that thrived in the challenging conditions of the Ice Age for a very long time. The global dispersal of modern humans, Homo sapiens, during the Ice Age represents one of the most remarkable chapters in human history. Originating in Africa, our species embarked on a series of migrations that eventually led to the colonization of every habitable continent, adapting to diverse and often extreme environments along the way. This spread was not a single, rapid event, but a complex process involving multiple waves of migration over tens of thousands of years, significantly influenced by the fluctuating climate and geography of the Ice Age. The earliest evidence for Homo sapiens outside Africa dates back to around 180,000 years ago in the Middle East. However, These early excursions appear to have been localized and did not lead to widespread global expansion. The main out-of-Africa dispersal that led to the global colonization is generally thought to have occurred in a major wave around 70,000 to 60,000 years ago, possibly along coastal routes, following abundant marine resources. This initial wave moved into the Arabian Peninsula and then branched out. One branch moved eastward, following the coastlines of Asia. This route would have been particularly advantageous during the Ice Age when global sea levels were significantly lower due to vast amounts of water being locked up in continental ice sheets. This drop in sea level exposed vast stretches of continental shelf, creating new coastal plains and potentially connecting land masses that are now separated by water. These exposed coastal areas provided rich marine resources, such as shellfish, fish, and sea mammals, which would have offered a stable food supply for migrating groups. The journey into Southeast Asia was facilitated by these lower sea levels. The islands of present-day Indonesia, Malaysia, and the Philippines were connected by a vast landmass known as Sunda. From Sunda, Homo sapiens made the challenging sea crossings to Sahul, the supercontinent that combined present-day Australia, New Guinea, and Tasmania. These were not land bridges but required intentional seafaring, demonstrating advanced cognitive abilities and technological skills for boat building and navigation. The earliest evidence for humans in Australia dates back at least 65,000 years ago, indicating that these maritime journeys were undertaken very early in the global dispersal. The colonization of Sahul involved adapting to a completely new continent with unique flora and fauna, including giant marsupials. Another major migration route from Asia led northward into Siberia and eventually across the Bering Land Bridge into North America. The Bering Land Bridge, or Beringia, was a vast treeless plain that connected northeastern Siberia with Alaska during periods of low sea level. This land bridge emerged multiple times during the Ice Age, acting as a crucial corridor for the movement of animals and eventually humans. The timing of the first human entry into the Americas is a subject of ongoing debate, with evidence suggesting initial crossings perhaps as early as 25,000 to 30,000 years ago, and a more widely accepted major migration wave around 15,000 to 17,000 years ago. These early Americans, known as Paleo-Indians, adapted to the cold, open steppe tundra environments of Beringia. Once in North America, Homo sapiens spread rapidly southward. The initial route may have been an ice-free corridor that opened up between the Laurentide and Cordilleran ice sheets in western Canada, or possibly a coastal migration route along the Pacific coast, which would have been ice-free earlier. Evidence for early coastal sites is difficult to find due to subsequent sea level rise, but it remains a strong hypothesis. From North America, humans continued their southward expansion, eventually colonizing Central and South America. The tip of South America, Tierra del Fuego, was reached by around 11,000 years ago, marking the complete colonization of the Americas. The colonization of Europe by Homo sapiens occurred later, beginning around 45,000 to 40,000 years ago. This involved encounters with Neanderthals, who had inhabited Europe for hundreds of thousands of years. Modern humans brought with them new technologies such as blade tools and advanced hunting techniques. They adapted to the cold European Ice Age, utilizing tailored clothing, sophisticated shelters, and mastering fire. Their artistic expressions, such as the cave paintings of Lascaux and Chauvet, demonstrate complex symbolic thought and cultural practices. The spread into Europe was a gradual process, with Homo sapiens slowly replacing or assimilating Neanderthal populations over several millennia. The ability of Homo sapiens to spread across such diverse environments during the Ice Age was due to a combination of factors. Their technological innovations, particularly in stone tool production, e.g. blade technology, spear throwers, allowed for more efficient hunting and processing of resources. Their capacity for complex social organization, including larger group sizes and extensive social networks, facilitated knowledge sharing and mutual support. Their adaptability in diet, exploiting a wide range of plant and animal resources, including marine life, was crucial. Furthermore, their cognitive abilities, including symbolic thought, language, and planning, likely played a significant role in their success, enabling them to innovate, communicate complex ideas, and adapt to rapidly changing conditions. The development of specialized clothing, portable shelters, and efficient control of fire were also critical for survival in glacial climates. The global spread of Homo sapiens during the Ice Age was a testament to their remarkable resilience, ingenuity, and adaptability. It laid the foundation for all subsequent human history, populating the continents and setting the stage for the development of diverse cultures and societies that would emerge in the post-glacial world. The routes they took, the challenges they overcame, and the adaptations they made continue to be subjects of intensive research, revealing the incredible journey of our ancestors across a frozen planet. Stone tools are the earliest and most enduring evidence of human technology, providing invaluable insights into the cognitive abilities, subsistence strategies, and cultural practices of early hominins and modern humans throughout the prehistoric Ice Age. For millions of years, from the earliest toolmakers to the sophisticated artisans of the late Stone Age, stone remained the primary material for crafting implements essential for survival. The evolution of stone tool technology reflects a progressive increase in complexity, efficiency, and specialization, mirroring the development of human intelligence and adaptability. The earliest known stone tools belong to the Oldowan industry, dating back approximately 2.6 million years ago in East Africa. These tools are relatively simple, consisting of choppers, river cobbles from which a few flakes have been struck off to create a sharp edge. The flakes themselves were also used as cutting implements. The manufacturing process was basic. A hammerstone was used to strike a core, detaching flakes. This percussion method required minimal skill, but demonstrated a fundamental understanding of fracture mechanics. Oldowan tools were primarily used for butchering animal carcasses, breaking open bones to access marrow, and possibly for processing plant foods. Their invention marked a critical turning point, allowing early hominins like Homo habilis to access new food sources and gain a competitive advantage. Around 1.7 million years ago, a more advanced tool technology emerged, the Acheulean industry. This period is characterized by the iconic hand axe, a bifacial, worked on both sides tool typically shaped like a teardrop or almond. Acheulean tools, primarily associated with Homo erectus and later archaic humans, represent a significant leap in cognitive ability. Their creation required a mental template of the desired final form, careful selection of raw materials, and a more controlled flaking technique. Hand axes were versatile tools, likely used for a wide range of tasks including butchering large animals, digging for roots or water, chopping wood, and possibly as projectile weapons. Cleavers and picks were also part of the Acheulean toolkit. The widespread distribution of Acheulean tools across Africa, Asia, and Europe indicates the broad dispersal of their makers and the success of this technology. During the Middle Paleolithic period, roughly 300,000 to 30,000 years ago, the Mousterian industry became dominant, primarily associated with Neanderthals and some early modern humans. The hallmark of Mousterian technology was the leveloir method. This sophisticated technique involved carefully preparing a stone core by removing flakes from its surface in a specific pattern before striking off a final predetermined flake. This allowed for the production of flakes with sharp edges and consistent shapes, which could then be used as tools or further modified into specialized implements like scrapers, points, and denticulates. Mousterian tools were more efficient and specialized than Acheulean tools, reflecting a deeper understanding of stone properties and controlled flaking. Scrapers were used for processing animal hides for clothing and shelter, while points were likely hafted onto spears for hunting. The precision of the leveloir method indicates advanced planning and cognitive abilities. The Upper Paleolithic period, beginning around 40,000 years ago and primarily associated with Homo sapiens, witnessed a revolutionary diversification and refinement of stone tool technology. The key innovation was blade technology. Blades are flakes that are at least twice as long as they are wide, with parallel sides. They are produced from specially prepared cores, allowing for the efficient production of many long, sharp cutting edges from a single piece of raw material. Blades could be easily modified into a wide array of specialized tools, including burins for engraving bone, antler, and wood, end scrapers for hide processing, and projectile points. This efficiency meant less raw material was wasted and more tools could be made. Beyond blades, Upper Paleolithic toolmakers developed microliths, tiny stone tools that were often hafted onto composite tools like arrows, harpoons, and sickles. This modular approach allowed for greater versatility, and the creation of tools with multiple components. For hunting, spear throwers, atlatls were invented, dramatically increasing the range and power of thrown spears. Bone, antler and ivory also became important materials for tools, used to create needles for sewing tailored clothing, fish hooks, harpoons, and intricate art objects. The invention of the needle, for example, was crucial for creating fitted garments that provided better insulation against the cold Ice Age climate. The types of stone tools used by early humans directly reflect their subsistence activities. Hunting tools, from early choppers used for butchering to sophisticated spear points, show their reliance on animal protein. Tools for preparing food, such as grinding stones for plant processing, indicate a varied diet. Scrapers and awls were essential for processing animal hides into leather for clothing, blankets, and shelters, crucial for survival in cold environments. Burins allowed for the creation of bone and antler tools, expanding the range of materials available for technology. The evolution of these tools illustrates a continuous drive towards greater efficiency, specialization, and adaptability to diverse ecological niches. The study of stone tools, known as lithic analysis, involves examining their raw material, manufacturing techniques, use-wear patterns, and distribution at archaeological sites. This analysis helps reconstruct ancient human behaviors, migration patterns, and technological capabilities. For example, finding obsidian tools far from their geological source indicates ancient trade networks or long-distance travel. The development of increasingly complex and specialized stone tools over millions of years is a tangible record of human ingenuity and our species' remarkable capacity for innovation, which was fundamental to our survival and spread across the globe during the challenging conditions of the prehistoric Ice Age.